go from current slide. And here's a couple of announcements. One I don't think you've heard yet, and this sounds like a great program opportunity for anyone who might need it. If you know of anyone who has or could potentially be having a tax problem, okay? You haven't been able to resolve with the IRS. The Taxpayer Advocate Service will assist practitioners in person in its upcoming problem-solving day. The Taxpayer Advocate Service Problem-Solving Day will be here at Austin State Community College on this campus, Bessemer campus, right next door over on this side in the Mill-South building. Okay? English?
Smith.
Smith.
Yes, sir.
Okay. Parent, right?
Yes, sir.
Excellent. Thank you. All right. They will be here in the Mill-South building. That's the, if you've driven around the perimeter, you might say, of the campus here, of the A building anyway, that circle sort of goes around the A building, just on the outside there, the whitest looking building, that's the Mill-South building, okay? In the Mill-South building, on the main floor, there's the lower floor, but on the main floor, at one end is a place called the One Stop Center. That's where they'll be Tuesday, March the 31st, that's the Tuesday after we come back from spring break, from 9 in the morning until 2 in the afternoon. Now, the partners here are our workforce development area, the Alabama Asset Building Coalition, the West End Community Volunteer Tax Assistance. That's free, get this, free income tax preparation. Absolutely free, okay? If you're interested in this, Ms. Brenda Thomas, I believe she's in Mill-South building, or is either Miss or Dr. Dorothy Henry, I think is either in the Mill-South building or up on the third floor here, one or the other. The Taxpayer Advocate Service, TAS, will be available to assist taxpayers with tax problems they've been unable to resolve on their own with the IRS. That sounds like a great service. Our goal is to provide personalized, step-by-step guidance. If your tax problem meets our criteria, their criteria, we'll assign a case advocate to work directly with you. Sounds like a great program. Now, the other partners here, the Alabama Asset Building Coalition, the AABC, supports IRS's VITA, that's Volunteer Income Tax Assistance, Voluntary Income Tax Assistance, and the TCE, as if they don't have enough initials here, that's Tax Counseling for the Elderly. So this doesn't have to be you, okay? It doesn't have to be even a member of your family. It can be anyone in the community. If you know of anyone, a family member, a neighbor, friend, someone you go to church with and a club with, anything such as that, that might need some help, any kind of help. They may not have had a problem in the past, but the new tax laws, the forms may be too confusing for them. They're just, it's getting too difficult to do. Let them know about this, okay? The AABC will be available to help taxpayers file their last year's and this year's both state and federal returns, okay? So it's a great service. These are two different services here, okay? And that one's pretty great in itself. Some conditions apply, and you can find them at AABC's website. The Taxpayer Advocate Service is an independent organization within the Internal Revenue Service, okay? Can you get your name, please? Capri, got it. Do you pronounce the R as a Capri or Capri? Huh? Okay, you don't hear the R. I didn't know. My hearing's so bad I didn't know exactly if you were saying it with the R or not. Okay, the first R anyway. Okay, within the Internal Revenue Service. TAS helps taxpayers resolve tax problems, recommend changes to prevent further future tax problems, and protects the taxpayer's right. They don't report on you. Anything you say to them is in confidence. They're part of IRS, but they're independent. They don't pass along anything. So their services are free to any taxpayers who are experiencing a financial hardship or having financial difficulties because of a tax problem. They're trying but haven't been able to resolve an IRS tax problem, or that might believe the IRS system or procedure just isn't working the way it was supposed to. So you can learn more about it at their website. I've got that up here. This is a long, involved flyer, but the information is great. So be sure to let anyone you know who could take advantage of this know, because it's free, absolutely free. Now, the others, I can't remember if I did this one last time or not. I know that a bunch of you, in fact, just about every one of you, were probably in first mini-term courses, right? Now, if you were, and some of you were off campus, I know that, but if you had student course evaluations to do, then they were late getting them out there, so if you haven't done them for the first mini-term classes, please do them. Please do them, because they were very late opening them up, and we need to have those. It helped. I'm a department chair. I'm a math department chair. It is later this spring and into the early summer, I'll be doing evaluations on every employee, full-time and part-time. I don't get to watch every employee teach. I go to the student course evaluations, get a lot of my input when I'm doing evaluations by employees, okay, of people in the department. All right, any questions? Anything up till now? All right, let me give you a quick recap for any that, I think all of you were here last time, but in case you weren't or you didn't hear it all, we finished chapter 1 last time. So today, starting at 3:15, we will start the lab on chapter 1. Now, it's a long lab. It's the longest we'll have. Shortest chapter that we're covered, and yet it's going to be the longest lab. Pretty involved, but y'all can do it. It's not going to be that difficult. It's just sort of long, okay? So we'll do from 3:15 to 5:15. At 5:15, even if you haven't finished the lab, we will halt, and then I'll give you a chance to do your first test, the chapter 1 test. Now, I can't remember if I said this or not. If you listen to the YouTube videos, which I hope you did, but if you didn't listen to those, let me say it now. You can bring with you to every test you take in this course, that's this coming test today, every chapter test, even the final exam, a formula and equation sheet. Anything you want to write down on a piece of paper, you can bring with you to the test. So if you have a few minutes today, break time or something like that, if you haven't worked on up for chapter 1, you might want to jot down some stuff. Anything you want to write down on a piece of paper, you can have. Okay? So the last 30 minutes, once Ms. Lewis gets here, will be the test. Okay. On chapter 1. Okay. Now, any questions? Whatever you want to have on a piece of paper. Yeah. Real good things to look at, in my mind anyway, would be right at the end of chapter 1. I don't know if certainly the equations that were listed there, and things you might pick out that this doesn't have as many equations as most, but anything, yeah, from your notes, from the book, anything, even examples, whatever you want to write down. If you want to draw a picture of Miss Florence Bascom, you can do that. I don't care, anything you think might be helpful. Okay? I just lost my place. No, there we are. All right, so any questions? Okay. Then let's get going on today's class. Now, where we left off last time, I'm having to be very ginger over here with my cord because it's flicking on and off some, but now it's pretty solid, but it's right in the way of writing, so that's what I'm a little bit slow about here. We had done this slide describing motion, and we hadn't quite gotten to, well, this is they just don't give me lots of white space. Here's some. We'll start here then. The driver of a car, this is example 2.1 on page 28. Now, if I think your book probably still has pretty close to the same page numbers as mine does. Does your 28 have in the upper left column a blue? Oh goodness, I think that's Zach. It looks a lot like him. Okay. You still good with Zach? Okay. I thought they got you back on the old job again or something. Okay. All right. What we're doing now is still under, well, I guess measuring motion would still be appropriate for it. So 2.1. I was going to say, does your page 28 look like this? Yeah, okay, so we're still on the same page numbers. I think it gets up to chapter 6 when we'll probably deviate page numbers. All right. Here it is. Remind me of your name? Drew, got it. Okay. All right. Does anyone else come in while I wasn't paying attention? You didn't hear me acknowledge you. Okay. So, on page 28, top of the second column, example 2.1. Okay. Well, let's see. Actually, let's hold off on this for a moment because I think the book slide set sometimes doesn't go along with the book too well. So let's pick up here. I think we did this slide last time, right? Okay. I think this is still describing what we're going to do, describing motion. Then we'll get into explaining motion, but that comes in sort of the middle third of the book, of the chapter. So just an idea of what that's going to cover is this. The basic ideas in explaining motion, and this is why I thought this was a good place to stop last time. Forces, and we're going to get to that in a couple of pages. Inertia and mass, and we'll talk about those a page or two later, and then we'll talk about Newton's laws. Okay, all that's coming later. This is just sort of looking forward to it. Then the third part of the book, of the chapter, first part is describing motion. We're going to still get to that. Then we'll do explaining motion, and then we'll do applications. And those will include momentum and impulse. That will be in the third. Circular motion, that will be there. Newton's law of gravitation. Boy, Newton's all over the place, isn't he? 3 laws of motion and his law of gravitation. As we said, Galileo and Newton, they were the ones that started the scientific method, basically. So that's where many people count science as beginning. So we'll talk about his law of gravitation, and then we'll get into the example of that, or applications of Earth satellites. Okay. So that will be coming in the middle part. Now we're in 2.2, which is measuring motion. Okay? We talked about this in a previous slide. Now we're actually going to do it. Okay? 2 fundamental components of motion. Now, I described that last time. Y'all remember? If something's moving, 2 things are happening. 1, you have a change of position. Number 2, it took a certain time for that change to occur. So those are the 2 fundamental components. A change in position, we can call that a distance if we're just talking about a how much it changed, or we can talk about displacement if we're talking about not just how much it changed, but in what direction it changed. Distance is a scalar quantity generally. Displacement measures the same thing, but it's a vector quantity, including direction. And then the second is a change of time. Now, in a lot of what we're going to be talking about in the whole course, we're going to be dealing with changes. If something is static and just sitting there, you can do some things with it. You can measure it and do things like that. But really, physics, in many ways, involves change. All of Newton's laws were involving changes. Okay? So, I'm going to give, I'll wait just a few minutes, so I'm going to give a symbol that represents change. And we'll get to that shortly. Okay? Now, we didn't do this slide, did we? Seems like I've taught the course many times, but I thought we did this one, didn't we? But that must have been the last time. Okay. Here's a car going down the road. Okay? This must be an unusual scale here. Now the Eric's here. Because if indeed this is a mile, that's just about the length of the car. Okay, no, obviously the scales aren't the same. But the distances here, here's your clock up here, and it shows that these are minutes, not hours, okay? Total elapsed time between this position and that position is 1 minute, then another minute, then another minute, then another minute. So the time interval is 1 minute between each of these. The distance traveled, starting at 0, travels 1 mile in the first minute, another mile in the second minute, another mile in the third minute, and another mile in the fourth minute. Going along, looks like constant speed. You can't tell for sure, but at least on this scale, it looks like constant speed. Okay? How fast is that car going? I thought that would be an easy answer for most of you. 60 miles an hour, because it's going a mile a minute, and that means in 60 minutes it would go 60 miles, if it kept up this rate. Now, we can't guarantee it will, but in those first 4 minutes and the first 4 miles, it looked like it was going on the average of a mile a minute. Okay? So, there are 3 important combinations they have here of these lengths in time. Anyone think of what they might be? What you get if you divide distance by time. I think I heard it. Didn't say it? I thought you did. Speed, of course. Distance divided by time is speed. So the first thing you can derive from a change of position and a change of time is speed. In this case, the change of position is the distance traveled. Okay? Distance being a scalar quantity, you're not worried about direction, just how far did you go. Okay? And how long did it take you to get there? That would be speed. Now, so it's change of position over change of time. I promised you I would give you the symbol for this. Here's what I typically use, and you'll find me using it sometimes without describing it, but here's what it is. Change of distance over change of time. Now that is a delta. Delta means difference. Okay, so let's go back to this slide. And what is your change of distance between here and here? Not that hard. 3 miles, exactly. How we usually do, the delta means a difference, so it's final minus initial. Okay? Always final minus initial. That's what delta means. So if it's from here to here, what does that do? 2 miles. 4 minus 2 is 2. Okay? So your delta D would be change of distance. Delta means change in or difference in. Change of time, what would the change of time be between here and here? 3 minutes. 3 minus 0, here and here. 2 minutes. 4 minus 2. Same, actually the same numbers here, but now you're dealing with dimension quantities. So your speed is usually in this case, it would be miles per minute. We're not used to talking about miles per minute, but in this case that would be because your delta D is in miles and your delta T is in minutes. Miles per minute. 1 mile per minute. Okay? So that's one way to express speed. They usually leave off the delta. They'll just say distance divided by time, which is okay. Okay? Just understand it's always a change. Because if it made a distance, that meant it started somewhere and ended up somewhere else. So, unless you're going in a circular track, and then you wind up the same place you started, maybe. I don't know. Okay, but there's your speed. The second of these is velocity. Wait a minute, isn't that the same thing? Why not? What does the velocity involve that speed did not? Anyone remember? I think we mentioned it last time. Say again? Gravity? No, not in this case. That'll be a good answer later, but not right now. Not mass. There's no mass. Say again? I can't.
Weight.
No, not that either. Direction. Direction. Velocity is a vector quantity. The direction matters. Okay? Now, the book uses the same symbol for both. They use V for velocity and V for speed. You just need to make a distinction there most of the time, but the book isn't going to make a special one. And if I was doing this correctly, I would say change of displacement. With an arrow over it means it is a vector quantity per unit time. Time is not a vector quantity, so that's just over time. Same units too. Miles per hour, miles per minute, feet per second, meters per second. Same unit, distance over time. Okay? Now, anyone want to make a guess what the third one is? I think we mentioned it last time. Here's what we do in physics a lot. Get used to it. Once we have a quantity, like position, we'll say, what happens when you do a time rate of change of position? Well, you get either a speed or a velocity. And then we might ask ourselves, once we got a velocity, what happens if you get a time rate of change of the velocity? Will be when you're on the highway and wanting to change your speed, what do? Accelerate. So that's acceleration. Okay? So acceleration is the change of velocity per change of time. That's what acceleration is. Acceleration is change of velocity over change of time. Okay? Now, that will lead itself to different ways of writing some equations and formulas. We'll get to those a little bit later. But that's the basic concept of an acceleration. Now, what units would be typical for velocity? This is the unit part here. Just name one. There's bunches you could pick from. Name a set of units that you could use for velocity. Miles per hour. Okay. And what change of time would you want to have down here? Okay, in the denominator, delta T. Yeah, okay, you might have that in second. Okay, and we used this example last time. Remember, somebody had a vehicle he said could do 0 to 60 in 2 seconds or something like that. That was an acceleration. That's what you're describing. How it's changing its speed, how long it took it to do it, that's an acceleration. Now, most of the time we're going in the book, we're going to be using units that look more like this. Meters per second per second, okay, or feet per second, okay? Either of those would be fine. Those are sort of awkward to write, so we sort of shorthand that to be meters per second squared, or feet per second squared. If your time difference is the same unit, then just square it. Because I don't know what a square second looks like anyway, but that's what we typically use. Okay? Is that making sense? And this isn't the first and the last time we're going to do this. It may be the first time, but it won't be the last. We're going to come up with another quantity soon. And then we'll say, well, what's going to happen if you take the time rate of change of that? And then we'll have something else. What happens if you take the time rate of change of that? You'll keep coming up with new concepts, new things to measure. Okay? And a lot of them make pretty good sense too. All right, so let's start with the speed part. Oh, I'm sorry. Say again? Okay. Okay, take your time.
How you doing, baby?
Okay, doing pretty well.
A test last week?
No, just a lab.
Oh, a lab?
Yeah, you did it the first day, didn't you?
No, I didn't.
Yes, you did. That lab 0?
Oh, lab 0.
Yeah.
So we hadn't had a test 1?
No, test 1 will be today.
Okay.
And lab 1 will be today. Lab 0 was last week, lab 1 will be today. And by the way, there is a faculty meeting this afternoon, but because I'm with this important group of people in this class, I can't go. But, yeah. I'm not going to ask, what did you say? Okay. I know better than that. Okay. But I'm wondering what's going to come out of that meeting because of what is going on. No, I'll find out.
2 weeks of spring break.
Huh?
2 weeks of spring break.
Oh my goodness, I didn't know we had such comedians in the class. Okay, no wonder I don't want to leave. Okay, now.
Can we take the test Tuesday and you go to the faculty meeting?
What's that?
Maybe something that's very important.
Hey, you know what? I'll see my boss tomorrow and he'll tell me everything that goes on. If he doesn't sleep through it. No, I mean, we wouldn't do that. Okay. Here's what I'm worried about. Okay? And it's not really worried, but, concern may be a better word or something like that. I think I told y'all last time, okay. And I believe I may have even told you this too. Maybe not, because I don't think I knew that. 2 days ago, maybe, I heard that there was a student here at Lawson whose parents just got back from a trip, and then they both got sick. Okay. Okay. It's nothing to worry about, but guess what? It's coming. It's going to get here. There's no doubt about it. My wife's an epidemiologist. She studies diseases. And she's been watching what happened in these other countries, China, South Korea, Japan, Italy, Iran. Iran's tough because they don't have good numbers there. And she's watched the growth of the disease. The U.S. got started late because we're oceans away, but guess what? We're on the same trajectory every one of these other countries is on, except possibly 2, and one's not a country, Hong Kong and Singapore. I heard this morning that they, as soon as they heard about it, they started precautions, and they started them seriously, and that they have slowed their rate way below what the other countries have been. Yeah.
I heard that someone in North Korea got the coronavirus and they were executed.
What's this?
North Korea is executing.
Where is this?
North Korea.
North Korea?
They're executing people with China.
All right. Mark that off my bucket list, okay? I don't think I want to go there, okay? Oh, it never was on there, okay? Sorry, that was somewhere else. But it's going to be here. In fact, it probably already is here in Alabama. Guess what? Hardly anyone has been tested in Alabama, okay? If they tested, they'd find out we already have a lot of cases. What I was saying about this gal who's here at Lawson, her parents just got back from a trip overseas to one of the countries that has had an outbreak. I don't think they knew they were having an outbreak when they were there, but they got back, and then they've come down with really bad coughs and stuff like this, and yet they refuse to go to the doctor, I think because they don't want to know. But the thing is, the odds are if they went to the doctor, they wouldn't be approved to have the test because we don't have enough tests. And the tests are fairly expensive. But so it's a mess. And then I heard this morning, and I haven't heard this confirmed, that there's at least 2 students that have been confirmed at Jeff State. But I haven't heard that on the news, so I don't know if that's true. You probably heard a professional basketball player came down with it. And therefore they suspended games for a while now. I don't know how long. Because they don't want their other players to get it, and they don't want the fans to get it. The NCAA March Madness, if the teams play, they're not allowing anyone in. They're just being on the court playing against each other because they don't want people exposed. So that may be what they're going to be talking about in the faculty meeting today. I don't know, but I'll find out tomorrow. And your instructors will find out today too, and you'll probably hear about it Monday, okay? Whatever they decide. I did hear this. Sanford is having, after spring break, only online classes. They're not having any students come back to campus after spring break. Just do the rest of the term in online. I heard someone else say we might be doing that for summer. I don't know.
How long do you suppose it's going to take to respond? How worried am
Okay? Boy, that's a loaded question, isn't it?
Yeah.
Judging by how I've seen and heard and sensed responses before, I'm guessing we'll be about the last to make a decision. I don't know. Maybe they'll announce today. I don't know. But it seems like most of the time they wait and see what everybody else does, and then they say, okay, let's do that. But I don't know. I shouldn't be talking badly of them because they may already have a plan in place. I do know this. Dr. Shawanda Thomas is in charge of the STEM program over on the Birmingham campus. She teaches here, her main office is here. She's here Tuesday, Thursday, over there Monday, Wednesday, Friday. And does anyone know what Saturday is? Does anyone know what date of Saturday it is? Okay. Well, it's Pi Day, 314. Okay, it's Pi Day, and because of the STEM program, they would plan to have STEM Pi Day activities, and they're inviting in a bunch of high school students and things like this to come and participate in the STEM Pi Day activities. Dr. Thomas came to see me maybe between my last 2 classes, and she said, Dr. Ward, our president, has called and said he wants to talk with me about Saturday's activities. I've got to go to the Birmingham campus. I won't be on campus the rest of the day. My guess, they could catch me. So I wouldn't be surprised. I'm wondering, we were also planning Saturday on this campus to have a whole bunch of high school students in. They have a name for that one too. And so far I haven't been able to get any math instructors to volunteer to do it. So I was going to do it, but my wife said, not with my immune system shot. So that's the other thing I'm going to talk with my boss about tomorrow, that I don't think I can afford to do it. Yeah.
So you have an opportunity to talk to your boss today?
Probably not today, tomorrow. See, by the time this class gets off, everybody's going to be home.
But did you say you had a meeting with them today?
No. They're having a faculty meeting today, but I would rather be with you guys.
But I
No.
Can we take our test Tuesday, like first thing Tuesday?
If you feel like you're not ready for it today, you can take it anytime during my office hours. Okay? Monday, Tuesday, Friday, anytime you want to take it. But it's going to be during office hours, not during class.
Office hours on Friday?
Friday on the Birmingham West Campus, 8 to 12.
Okay.
And you know where Dr. Pruitt's office is over there?
I find it.
Okay, it's in the B building Y'all did my syllabus. Y'all did that last year. You know all made this stuff. I should be asking you what my office hours
What are your office hours?
Okay. On Fridays, it's 8 to 12 on the Birmingham West Campus in the B building. That's the academic building. If y'all know the Birmingham West Campus, it's that long building. There's a quad of buildings. 4 buildings sort of make a rectangle. And the back building, the long one, that's the B building, the academic building. It's the end toward the gym, the tennis courts, and the baseball field. That end of the building. When you go in the building, you either go down half a flight or up half a flight. Go up half a flight. When you step on the top step, the door immediately to your right is Dr. Pruitt's office. And that's where I'll be 8 to 12 tomorrow. Now, they may have meetings called for us tomorrow to discuss what they're talking about this afternoon. But whatever, if I'm not in a meeting, I'll be there. Okay? So if you are going to take your test tomorrow, please let me know today so I will take a test with me so you can take it over there. Okay? Because I won't typically take all my tests to the Birmingham campus. So just let me know and I'll take it. I've got 3 tests for students in my Math 112 class. Okay? Now, so.
What about Monday?
Okay, Monday, my office hours are 8 to 10 on Monday morning here on this campus. Monday through Thursday, I'm here with one small exception, and Friday, I'm on the Birmingham West campus. So Monday, 8 to 10, and 3:45 to 6. That's the day with the most office hours. Just a little bit more. Okay, Tuesday, it's like today, and I have 8 to 8:30 in the morning, and then 12:45 to 1:15. That's when I eat lunch, right before this class starts, and then right after this class is over.
Okay, well, I'm telling you, I'm gonna do mine on
Monday, okay, either 8 to 10 or 3:45 to 6. If you don't know where my office is, everybody knows, you go out the door, hang a left, go down that half flight of stairs, go almost the end of the hall, right before you get to the stairwell, the office there is 265. Same side that we're on here, 265, right across from the orientation classroom. Okay, right across from that. Okay. And then Wednesday is a lot like Monday, except it's only 8 to 10 in the morning. So Wednesday afternoon, that's one exception. As soon as I get out of my 3:45 class, I have to book it to the Birmingham East Campus for a physics class that goes 4:30 to 6:30. So that's why I don't have that 3:45 to 6 of the whole Birmingham East Campus on Wednesdays. Okay, so you just got my office hours again, even though you wrote them all down in your first lab or your 0 lab, but there they are. Okay. Somehow we got off onto that, but anyway, it is a concern, and it's sort of a.
It needs to be addressed.
Huh?
It needs to be addressed.
Yeah, well, that's why I say I think it's going to be talked about this afternoon. We'll all get the word. I'll get it tomorrow, okay, and find out for sure what's going to go on. As sure as we can know, yes.
Do you mind like giving tests at the beginning of the class?
Okay, I thought I sort of explained this last time. Here's why I do what I do. Because if we had either lab or test at the beginning, and say one lab group or some people taking the test took like 2 or 3 times as long as the others did, then everybody else is sitting around waiting for them, and then we all have to start over again. Whereas when we have class, we all have class, end it, have lab. When you finish it, you either are going home afterwards or taking your test afterwards. Then when you finish that, you get to go home. You don't have to sit around and wait for other people to finish. So that's why I do it this way. Otherwise, people really get irritated and sometimes leave, and that's counterproductive. Okay? So, now, is a reason because you have to leave early or something?
I stay until school. I have to leave at 5.
Okay. If you'll let me know a half hour before you have to leave, then I'll give you the test and you can go to another room and take it. Everybody's got a half hour, so if you have something like that. Now, if it's a lab, there's a get with someone else, ask someone to get the data for you, then you work up your lab, you can do that. Okay? So if we're having a lab that day, you can get the, well, yeah, you'll be here for most labs because they start usually at 3:45. So you'll have the lab, and anything you don't get done, ask one of your partners in the lab. You'll always be in teams. Ask one of your teammates to get any additional data for you, and you can get it from them. Because labs, you work together. That's part of what lab is cooperating with each other. Okay? But the test, if you have to leave before the test, let me know 30 minutes before you have to go. I'll let you take it early. Okay.
But this first test, I'll just take it later.
I'm sorry?
This first test,
Yeah.
I'll be here most of the time, but the first test, I'll just take it.
That's fine. Anybody, if you don't feel ready for a test, you can always take it, but you need to do it during my office hours. Okay? All right. Now, I realize I can't. See, usually that first day of class, I go over everything about the formula equation sheets and all that kind of stuff. I realized we didn't have class together, and I was encouraging you to watch the YouTube videos, but I'm just guessing a lot of you didn't. Okay? I don't sort of blame you either. But anyway, all right. All right. Not that funny, Miss Lewis. Okay. All right. So that's what acceleration is. And guess what? As I said before, units are important. Displacement measured in some sort of length measurement. Inches, centimeters, meters, yards, feet, miles, furlongs, whatever. Time measured in seconds, hours, minutes, whatever. Speed is always distance per time. Meters per second, miles per hour, feet per second, whatever. Furlongs per fortnight, whatever. Okay. That's how you can tell velocity or speed, by its units. Okay. Acceleration, distance per time per time. Yes.
What's the little mark above the D again on velocity?
Okay, that's a vector symbol, meaning an arrow, meaning the direction matters. Most of the time, I'm not going to do that. The book doesn't do it, but when I am talking about the vector, I want it to be emphasized. I'll put that symbol there. Most physics books do. This is physical science, not physics, so they are a little slighter. Okay. Any questions on measuring motion? Then that was a long slide, wasn't it? Okay. So the first of these was speed. So you see, this is the general. Here's some more specific. What speed is, like we just said, change of position with respect to time. Delta D over delta T. Okay? Now, there's two types of speed you can deal with. I'm not talking about that kind. No, never mind. Okay. All right. There's average speed. Average speed would be like you were talking about if you were going on a long trip. Okay? I can remember when I got out of college, I got my commission in the Navy and had my orders and had to go to San Francisco from Georgia to catch a flight to catch my ship in Guam. Okay, so that drive across country in my old 71 Plymouth Duster, it seemed like it was, I guess it was a 71 Plymouth Duster. This was summer of 73. I was, figuring out how many miles I needed to make each day, how fast I thought I'd be driving, how long I would drive then, and stuff like this. That was average speed, okay? Total distance divided by total time. If I stopped for gas, if I stopped to eat or something like that, my average speed would go down, okay? If I hit somewhere out west where the speed limit back then was 75 miles per hour, the average speed would pick up a little bit. That's the most common measurement, total distance over total time. However, when Isaac Newton, I think he was approached by the guy who did planetary motion, Kepler, Johannes Kepler. And Kepler said, I've developed a set of equations that explains the planetary motion. And it explains them really, really well. Up to then, no system of equations had worked. He said, the trouble is, I don't know why they work. Can you give me the physics of why these equations work? So Newton had to figure out some way of doing it, and up to then, all they had was algebra, which could do average speed, change of distance over change of time. he found out he needed to know because the planets didn't always travel at the same speed. They're always changing, constantly changing their speed. So he had developed a new math that measured instantaneous speed. Okay? In this case, remember it's delta D over delta T. Now the delta T is going to 0. And can you divide by 0? No. Okay, but you can take a limit as you get closer to 0. That's instantaneous speed. Now, what devices would you use to, say, in your car to measure average speed? It doesn't have to be something part of the car, but like I said, going on a long trip, what device would you use to measure average speed? Okay, that measures instantaneous speed, because that's always varying with what you're doing. Your speedometer isn't, that's my punchline, you jumped into it, okay. The average speed would be your odometer. How many miles did you travel? And look at your clock, watch, or your clock, or your telephone, or whatever you look at these days to get time, and that would be your time. So you would use your odometer and some time device to get average speed, but your speedometer is basically giving you pretty close to instantaneous speed, because that could be doing like this, especially if you're in city traffic. You know, out on the expressway, you might have a peg somewhere as fast as you could go. Okay, and not get caught. Okay, so here's how the book defines speed. Like I said, they don't use the delta, they just say distance divided by time. I said change of distance over change of time. It's really the more precise definition. Okay? Now, they're not going to do this now, so I'm going to do it for you. Okay? Can you give me two other equations that mean the same thing as this, but written differently? And I think we did this last time, didn't we? Time is equal to time is equal to speed. Distance over speed. You got it. Distance over speed or velocity. Okay, I really like velocity better, but since they use speed here. That's absolutely right. How can you tell? Look at your units. Your distance is in, just make up a unit for distance. Meters, okay. And what's the speed using the same type units? Don't go to feet. Meters per hour, okay, that would be fine. If you do that, you get meters divided by meters per hour. That's what the division line is, right? Which is done as meters. How do you divide a fractional form? Oh, this is math, isn't it? Times, yeah, the reciprocal. Hours over meters. The meters cancel out. You got time in hours. Perfect unit for that. So units are your friends. They help you know whether you've got it right or not. Okay? So let's get those friendly units out of the way and do the third equation. What third equation could you get from that one equation? Pretty easy one, by the way. Distance equals speed or velocity multiplied by time. And again, units are your friends here. Look at units. What's units for speed? You use the same ones or different ones? Tell me. Second? Meters per hour. Okay, that's fine. And then when you use time, use the same unit. Meters per hour, sorry. Hours. Time's measured in hours. Hours cancel out. You wind up with meters. Great thing to measure distance, right? It works. They work every time. So anytime you see one equation like this, you got two others that you don't see. And they're there. And I did the triangles and circles for you, didn't I? Yeah, okay. I was hoping I was in the same class. Okay. So there is speed. Now, here's an example of average speed. This car has gone how far?
100.
100. Remember, delta is final minus initial. So it went from 50 to 150, that's 100 kilometers. Okay? So your delta D, that's why I like to use delta. Okay? The delta D is equal to 100, that is 150 minus 50 kilometers. And what's your delta T? Distance over time is what? 2 hours. 3 minus 1 is 2 hours. So what was his average speed? 50. Yes, don't forget your units. Okay, units are your friends. Don't leave them behind. Kilometers per hour. Now, does that mean the guy was traveling 50 kilometers per hour the entire time? No. He could have been going 75 or 80 or 90 is close to 60 miles an hour, isn't it? Could have been doing that part of the time. He could have stopped and taken a water break, okay? Or a loose water break, or something like that, okay? So, no, that's just his average speed. Hope he wasn't traveling that time all the time. Say again?
I thought you said take a break.
Okay. Okay, I couldn't hear that, sorry. Okay. I was waiting for her to take a picture too. Okay. I want to get out of it. Okay. All right. So calculate the average speed. So let me erase this so you can see how they did the calculation. Y'all did it really quickly. They'll probably take a little more effort to do. Okay. And now, here's another. Don't get this confused. When you see the bar over it, not the arrow, but the bar, that means average. Average speed or average velocity is distance over time. Question mark over question mark. So what's the distance? Whoa, they didn't show it, did they? Oh, they just left it blank, okay? But that's what we did, okay? Distance over time. They did it in the book and got the 50 kilometers per hour. They just didn't show it on the slides. I don't know why. All right. Now, here's something else you can do with stuff like this. Oh, I think I've already done this. Yeah. But let's do one other problem like it, or similar to it. Bottom of page 28, the left-hand column on 28. If V bar, that means average speed or average velocity, is 50 kilometers per hour, hey, surely they could have come up with something a little more creative than this. And the time traveled, T, or you could call it delta T if you wanted to, is equal to 2 hours. I think even I could figure this one out. What is left and what would you have? What would be the formula you'd use, even though you don't have to use it? Distance is equal average speed times time. Okay, and what would that be? 100 what? Don't just give me a number. Say again?
Kilometers per hour.
Speed was kilometers per hour. Distance is kilometers. Hours cancel out. Right? Kilometers per hour times hours, the hours go out. So you're left with kilometers. And that's what a good distance is. Kilometers per hour is not a distance. That's the speed or velocity. Okay? So units are your friends. Help them. Let them help you. Okay. Now I think we're ready for example 2.1. So let's see what we can do to find room to write it. We might have to write on this one. Let's just see. Okay, wait. That looks like a good place to write. Okay. All right. The driver of a car moving at 72.0 kilometers per hour. What is that a measure of? 72.0. I'll write it down. 72.0 kilometers per hour. What does that measure? Say again?
Speed.
Speed, you're absolutely right. I'm going to call it SPD so I don't have to write it off. Okay? Drops a road map on the floor. I would say floorboard. I don't know why they said on the floor. Okay? It takes him 3 seconds to locate and pick up the map. So what's that a measure of? Time. Seconds. Okay? That's his time. Okay? How far did he travel in that time? So what's going to answer that question? How far? Distance. That's the unknown here. But before we get started, folks, what do you notice? Anything? Yes, what do you need to convert?
Seconds to hours.
Okay, either seconds to hours or hours to second, either one. Now, what do you think the distance do you want to measure in? You want to measure that distance in 3 seconds in kilometers? That doesn't seem like the right, that's such a long distance for such a short time. So you might want to use, rather than kilometers, smaller unit. Second? Someone mumble it? Meters. Why not meters? So let's, instead of converting the kilometers per, the seconds to hours, let's convert the kilometers per hour into meters per second. Because we want seconds anyway, and we'd like to have meters anyway. Okay? So I'm going to come up here and do this. 72.0 kilometers per hour. Now, I'm going to do it the way I like to do it. If you have a better way, a way you understand better, by all means use it. But I like to use what some people call the train track method. You have a conversion factor there, maybe another conversion factor there, maybe even a third conversion factor here. And what you're finally trying to get to is meters per second. You're trying to get from kilometers per hour, which is distance over time, to meters per second, which is also distance over time. So you've got either one or two conversions to get from kilometers to meters. One, I think you can probably do. And hours to seconds, that's where you're going to have either one or two. So what do you want to start with? I really don't care. Either kilometers to meters or hours to either minutes or seconds. Pick one. Hours to second. Do you know the conversion factor for that?
I do not.
You do not. What do you know the conversion factor to? Hours to minutes. So let's do that one first. Okay? Now, notice every conversion factor I have two lines here. This one's for numbers, that one's for units. This one's for numbers, that one's for units. This is for numbers, that's for units. This is for numbers, and I've already got the units there. I already got the number here and the units there. Okay? So, here's my suggestion always. Always put the units in the place, later match the numbers with the units. So if you're going from hours to minutes, I want to put hours in one place and minutes in the other. And which do I put where?
Hours goes in the first
On top?
one. Yes.
Yes. Okay. And minutes on the bottom? I like that idea because now the hours will cancel out. Okay. Now you match the numbers with the units. How many hours in a minute or how many minutes in an hour? Say again? 60 which? 60 minutes is 1 hour. Got it. Done. Now what you want to do next? Minutes to seconds. Okay. Which are you going to put where? Seconds on top?
No, seconds on the bottom.
Seconds on the bottom, minutes on top, because you want to get rid of the minutes, right? They need to cancel out. Minutes over minutes is 1, right? Okay? And what's the conversion there? How many minutes in a second or how many seconds in a minute? 60 which? 60 seconds is 1 minute there. Get the units in their place and match the numbers with that. And the one last one you got to do is what? Say again? No, you already got the seconds. That's fine. You want to do? Yeah, to meters. Kilometers to meters. Which unit is going to go where?
Kilometers at the top, meters at the
Kilometers at the top, meters on the bottom. That gives you kilometers squared per meter second. I don't think so. So what might we do? Meters at the top and kilometers at the bottom. Let's see how that does. Always get the units in place. Ha! Yeah, the kilometers will cancel out now, and the meters are right where you want them to be. And the seconds right where you want it to be. Now, how do you convert meters to kilometers or kilometers to meters? What's the conversion? What does kilo mean? Except on the street. 1,000. Okay, so which goes? Where does 1,000 go? Really, 1,000 kilometers is 1 meter. Wow! I can run a meter in, 1,000 kilometers, which is 1 meter. I can do that. I think you got it backwards. That's 1,000 meters, called 1,000 means kilo. Kilometer, 1,000 meter in 1 kilometer, right? Okay. Now you multiply numerators and divide by denominators. And since I don't have a calculator, I like to do it this way. I'm going to wipe out a 10 and a 10 there, and another 10 and another 10 here. Okay, that was easy. Then I'm going to go 6 into 72 would be 12. And 6 will go into 12 twice. And that gives me 20. 2 times 10 is 20 meters per second. Now you do it on your calculators and see if you get the same thing. Might take you a little longer, but you can do it. 72 times 1,000 divided by 60 and then divide by 60 again. And what do you get? Got a calculator? Please, and please on your test, bring a calculator. I don't come equipped with calculators, and it'll just make your life a little easier if you have a calculator. You can do it by hand if you want to, but it's a good idea to bring a calculator. Okay? So if someone will do that, 72 times 1,000, I can do that in my head, 72,000 divided by, and I can multiply 60 by 60 and get 3,600. And what do you get? 20, yes, okay, it did come out right. So that's now my speed is, oh, I forgot to do this. You had 3 significant digits everywhere, so let's keep 3 significant. This is the same as 20.0 meters per second. Okay? Now let's do the formula. What's the equation for distance? Okay, V bar times time. And V bar is your speed. Your speed. Average velocity. Okay? So this is 20.0 meters per second times 3.00 seconds. Seconds cancel out. Yes. Okay? And what does that give you? 60.0 meters. So in that 3 seconds, how far did he travel? 60 meters. Now what is 60 meters approximately? Just give me a general idea. It's longer than 2/3 of a football field. Right? Football field is 100 yards. A meter's longer than a yard. Not a lot, but a little bit. So this is probably more than 2/3 of a football field. It's about 65, 70 yards. Hey, he traveled that far in his car when he wasn't looking. Okay? A lot of things can happen in that distance, right? So that's why you be very careful. And by the way, 72 kilometers per hour is not that fast. Okay? I think that's about 60, maybe, no, that's less than 60 miles an hour. Okay? All right. Any questions on that? And you'll see in the book, they calculate the same result. Now, they may have done, they converted the, I don't know what they did. Goodness gracious. They did their 72 kilometers per hour. Boy, did they ever do a strange conversion there. I never would have come up with it that way. But we did the same thing. All right, example 2.2. Any questions on that one before we lost it? Looked like I had a confusing look on the face. Got it?
Yeah.
Okay, good. All right, let's go to 2.2. Can I erase, or is someone still writing? Everybody got it? All right, so let's erase that ink. And let's go to example 2.2. A bicycle has an average speed. What's the symbol for average speed? Say again? V bar. Is that what you were saying? Please say yes. Okay. Bicycle has an average speed of 8.00 kilometers per hour. They seem to like metric, don't they? Kilometers per hour. Okay. How far will it travel in 10 seconds? What's 10 seconds a measure of? Okay, time. All right, here we go again. Got to convert the kilometers per hour to meters per second. And y'all remember how to do it, don't you? 8.00 kilometers per hour times blank blank times blank blank times blank blank equal how many meters per second? You can do any order you want to. Want to do it the same way as last time? Okay, how'd you do it? You want to do kilometers and meters? Which goes where then? Kilometers on top. Still kilometers on top, huh? And meters on the bottom. Oh, no, that won't work. Oh, okay.
And the meters on the top.
All right, meters on top and kilometers on the bottom. Okay. Kilometers on the bottom. And what's that conversion? 1,000 meters is 1 kilometer. Yes. Next. And you can cancel out your kilometers. What's next? Doesn't matter, but pick something. You got the meters where you want it. You got to get the hours to seconds. How are we going to do that?
So you do minutes to seconds.
Okay, let's
Or hours to minutes.
hours to minutes. Where do you put what?
Hours on top.
Hours on top, minutes on the bottom. How many goes where?
60 at the top.
Really, 60 hours is 1 minute. We're going to be here for a lot of minutes, folks. Okay.
1 hour.
Oh, yeah, we got it backwards. Okay. All right. I thought we could stay here a while that way. Okay. 60 minutes is 1 hour. Okay. And now the hours cancel out. And then one more conversion to get it right what we need.
Minutes to seconds.
Minutes to seconds. What goes where?
Minutes at the top.
Top.
And seconds
Seconds at the bottom. Minutes are going to go out. That's good. What numbers go where? Say again? 1 minute is 60 seconds. Absolutely. Okay. Now we could do some of the conversions I did before, but you don't have as many. So I would say let's just use your calculators. All right. You can do a lot of it in your head. That would be 8,000. I'm going to write it this way. 8,000. That's 8 times 1,000 over 3,600. Okay. And then I can wipe out the 2 sets of zeros here. 80 divided by 36, that would be 40 divided by 18, which would be 20 divided by 9. And I don't know what that is. Someone get it to me. 2.22. Is that right? Meters per second. Now, I think I would carry one more 2, even though we only have 3 significant digits, just because otherwise you're going to have some round off error. So let's carry it one more. What's your formula to get from, we did get our question here. How far will it travel? So what are we looking for? Distance. That's the unknown here. And how is distance related to average speed and time? is velocity times time. Average speed times time, and that would be 2.222 meters per second times 10 seconds. 10.0. Oops, you can't see my seconds. It's out there. Okay. And the seconds will cancel out that second, and that gives you 22.2. This time I'm going around the three significant digits, 22.2 meters. Okay? He went about a quarter of a football field in 10 seconds. Make sense? Not out of the question, right? All right, so there was examples 2.1 and 2.2. Okay? Okay, yeah. If you can read my sloppy writing.
You see the words?
What's that
Is
again?
that number 40?
This one right here?
Yeah.
Yeah, I wiped out the two sets of two zeros, and then I divided 80 by 2 was 40, and 36 by 2 is 18, and 40 divided by 2 is 20, 18, 9, and 9 will go to 22.222222222.
40 over 18 and 20 over 9.
Yeah, you don't have to do it that way. You can use your calculator or computer or whatever. I just didn't have one. Yeah. Okay. I had to use the little old gray cells, and they're not doing too well. Okay. All right. Any questions on speed then? This kind of speed. Okay. All right. So let's move on to. Oh, we already did this one. Velocity. Now, how does speed differ from velocity, or velocity differ from speed? Say again? I thought I heard someone answer.
Direction.
Direction, absolutely. Velocity usually incorporates a direction. Okay? It describes speed, which is how fast something is going, and in what direction is it going. Okay? For instance, this morning, I drove from home to work, and that was let's just say I averaged about 60 miles per hour because I had some time in town before I left Birmingham. I had time in town after I got off the expressway here. So let's just say I averaged 60 miles per hour. But I was going in a southwesterly direction from Birmingham to Bessemer. Okay? Now when I drive home, I'm going, let's say, about the same speed, but this time I'll be going in a northeasterly direction. So different velocities, even though the speeds are the same, because the directions are different, it is a different velocity. Okay? Make sense? Okay. The graphical representation for vectors is a length, which implies the magnitude, like the speed, and then an arrowhead, which gives basically your direction. Now, sometimes we're pretty generic and just do an arrow in any old direction, but that indicates it is a vector quantity. Okay. So here's one. This shows them in this way. Here, this car is going at 30 kilometers per hour east. What is that measure of? Velocity, because it has both a magnitude and a direction. Down here, though, this one's going at 60 kilometers per hour in the easterly direction. So it's twice the velocity, but they drew the arrow twice as long. So that's how they indicated a faster speed. But the arrow said what direction. Now this one's also going 60 kilometers per hour, just like this one is. The trouble is this one's going to the northwest, this one's going to the east. So those are not the same velocities. They are the same speeds, but different velocities because they're going in different directions. Okay? Does that make sense? Now later, there'll be more of a reason why we pay so much attention to direction. But the direction is important. These are same directions, different speeds. These are same speeds with different directions. Both of those different velocities. Okay? Even though these are obviously different speeds, this is same speed but different directions. So velocity is different. Okay. Everybody got it? Okay. Whoa. That's all they have on velocity in the book, one little paragraph. Okay. So let's move to acceleration. Just like what I said before, once you get a unit like like distance, take the time rate of change of distance, you get speed. Displacement, time rate of change of displacement, you get velocity. Well, once you got a velocity, acceleration is time rate of change at which velocity changes. Now, this book uses these two terms as if they're the same, motion and velocity. It's a little bit of a strange synonym, but really, the way this book uses it, they mean the same thing. If something's in motion, it's got to have a velocity. Got to have a velocity. Okay? It's the rate at which motion changes over time. Sometimes I'll use the time rate of change of velocity or time rate of change of motion. Now, three things can cause an acceleration. Your speed can change. You certainly are accelerating then. Your direction can change. Even though your speed is not changing, you're still accelerating when you change direction. Or you can have both speed and direction changing, and then certainly you're accelerating. But accelerations can also be negative, just like velocities are negative. If I'm going this way, I'm going in, let's say, a positive velocity. If I'm going this way, that's a negative velocity. Now I'm getting further from my goal there, okay? Because your delta D is final minus initial. If I was there at 10 and over here at 7, that's a minus 3, okay? Final minus initial. 7 minus 10 is a negative 3. So speeds can be negative, or velocities can be negative. Speeds are usually positive. Velocities can be negative, so can acceleration. Now, what do we mean by negative acceleration? Just give me an example. Did you negatively accelerate at all today?
No.
I sure hope so. Else, whatever you're driving on that road out there, you are still driving it, right? If you didn't have a negative acceleration, you had to change velocities in a negative direction, okay, to come to a stop, okay? So let me put it this way. What three devices in your car accelerate for you? The brakes as well as the accelerators. So you name two of them. What other device in your car will accelerate for you? The steering wheel is an accelerator. You don't think of it, but it, in a sense, in a really strange sense, it is. Okay? Anytime you change direction, you're changing velocity. When you have a change of velocity, you have an acceleration. Okay? Now, you tell me what my acceleration is, what I'm going to describe here. Tell me whether it's positive or negative. Positive, because I started slow, ended up fast. Change of speed was final minus initial. That may have been 7 meters per second here, 1 meter per second there. Okay? Now, what would this be? Well, wait a minute. If my speed was negative and it was a fast negative speed here, a slow negative speed there, let's make this minus 7 and that minus 3. Minus that final, minus 7, minus a minus 3, yeah, it would be, it's rather strange, isn't it? Those minus signs are out there to trip you up. That's the only purpose of their lives, is to trip you up, okay? So you can do all sorts of things. This would be a negative acceleration also, okay? And this would be, that's a positive acceleration, because this is a negative speed, but a small one. That's a large negative speed. So minus 1 minus a minus 6, that would be minus 1 plus 6 is a positive 5. Meters per second squared, or whatever you're using. So acceleration can either be positive or negative. Now, if the direction's changing, it's hard to say a direction with it because I'm doing one-dimensional motion here, positive or negative. If direction's changing, then you got two-dimensional motion. That's a little harder to describe, but it is an acceleration. All right, so here we have a car going from 30 miles per hour to 60 miles per hour. What's its acceleration? Oh, they didn't tell you a time, so you don't know. Okay, but what kind of acceleration is that? Positive or negative? Second?
Which one?
30 to 60. That's a positive acceleration. Final minus initial is a positive number. Your time is always positive. Have you ever gone backward in time? No. You wish you could, but you couldn't. Okay? Back to the Future was all fiction. Okay? You can't, oh, y'all don't even know that, do you? Okay? Way before your time. Okay? All right. Here, he started off going 60 miles per hour and then saw a cop and slowed to 30. No, that's not the reason. Okay? What's he doing there? Negative acceleration. Here, started off 30 miles per hour in this direction, but then wound up in 30 miles per hour in that direction. Is he accelerating? Yes, because he changed direction. And a change of direction is, in fact, if this is indeed positive, this is a plus 30 is the final, a minus 30 was the initial, and plus 30 minus a minus is plus 60. Okay, so yeah, that's definitely an acceleration. And how about this one? Started at 30 miles per hour, they didn't show this very well, and then wound up at 60 miles per hour there. Is he accelerating? Yes, he's changing both speed and direction, and this would be, if this is indeed positive this way, negative that way, that would be a plus 60 minus a minus 30, which is plus 30, which is plus 90. I don't know how long it took, but it took some definitely positive amount of time. Does that make sense? All right, good deal. Now, without being an example, they do give some examples, and let's just do one of these. When you just have straight line motion, it's pretty easy. Consider a car that is moving in constant straight line velocity of 60 kilometers per hour. So 60 kilometers, and they don't put any decimals, kilometers per hour. Now, that's what they give you. What is that a measure of? 60? It's a speed, or if you wanted to, in this case, when you talk about acceleration, call it a velocity. And which is that? That's at the beginning, isn't it? So let's call that V initial. Okay? Now, you could put an arrow over it because you're talking about velocity, but they're not calling it that, so we'll leave that alone. Okay? And when the driver accelerates he goes from this to 80. I say 80 and write a 6 again. There's something wrong with the old gray cells here. Right? Okay. 80 kilometers per hour. This is V final. Okay? F is final, I is initial. Okay? And suppose it takes 4 seconds for that to happen. So what is 4 seconds a measure of? Time. Your T or your delta T. I like to call it delta T. The book just calls it T. So what's your acceleration then? What's the acceleration?
Final velocity minus final velocity minus initial velocity.
Okay, yeah. I thought you were saying 5, and I was giving me the answer already. Okay, you got it. V final minus V initial. Your delta V is always final minus initial divided by the time interval delta T, which is 4 seconds. And your final was 80 kilometers per hour. Your initial was 60 kilometers per hour. And this was a over 4 seconds. So this was a 20 kilometer per hour difference in 4 seconds, and that was anyone do it? Pretty easy. 5 kilometers per hour per second. Not nearly as hot as his car is, but you know, it's going. That is an acceleration. Sort of an unusual unit, but that's what a lot of drivers use. Okay? And guess what, folks? They're not going to be able to accelerate at that rate for very long, because your speed is going to increase way fast. Okay? All right. Now, they have a little blurb at the bottom of this page. It's sort of an in summary. At the start, you were going 60 kilometers per hour. At the end of the first second, you were going 65. At the end of the second second, you were going 70. At the end of the third second, you were going 75. And at the end of the fourth second, you were going 80. And that's your final velocity. What can you say about that? I know I was just reading the... Say again? 5 kilometers per hour per second. You're right. And it's constant. Now, that's leading up to what this is leading to. Uniform acceleration is anytime you have constant acceleration. And that description I just gave to you, where every second was changing by the same amount every time, that sounds like a uniform acceleration. Constant straight line acceleration. Don't count turns in this, okay? Constant straight, that's uniform acceleration. Your average velocity is simply related to the initial and final velocity. If you're going at a constant acceleration, then, okay, I'm going to put two things together here. I think I'll erase this that we've got here, if I can find my cursor here. Okay. Now earlier we said V bar, average velocity, was what? Anyone remember? I know it was a long time ago, but at least 7 minutes, huh? What was this? Second? Average velocity, average speed. Distance over time. Excellent. Y'all got it. Now, what do they just say here? Average velocity. If you have uniform acceleration, constant straight line acceleration, your average velocity is just like your average test score. If you're taking 2 tests, what's your average? How do you get it? Add them together and divide by 2. Well, that's exactly what it says too, is simply related to initial and velocity. In that case, average velocity, if you have uniform acceleration, is equal to V initial plus V final divided by 2. Okay? That's all. Okay? So let's see what they say. Ah, there it is. In the way of my stuff. So now we have 2 ways to get average velocity. In the second lab we do, okay, we've done lab 0, and today we're going to do lab 1. In the lab we do next Tuesday, we will be doing average velocity and calculating accelerations, okay? And we will use this one. Yes? What's that again? Okay, you mean what I just erased? Once it's erased, it's gone, sorry. Yeah, I'm sorry. But I'll show you where it is. Oh, there it was. V bar is equal to D over T. Same one we had before. Okay. All this time I thought she was taking my picture. Okay. No, I'm just kidding. Okay. All right. Yes. Okay. She's saying that because she knows my immune system bad. I'm going to say, get out of here, lady. Okay. No, I'm not going to say that. Okay. Hope you feel better. All right. Now, this think I mentioned it to you before, likes to do the graphs, but they do very little with the graphs until it gets to lab time. And then they're going to have you graphing all the time. But, in the book, here is a graph. This is on page 28, distance over time. The slope of that is your average velocity. The slope of that curve, distance over time. Well, what is slope? Give me a definition for slope. Rise over run. Rise is vertical, run is horizontal. Distance over time, kilometers per hour. That's exactly what you get there. And if it's straight line motion, then that comes out exactly. Oh, this is a heavy one. Okay? Here, we have speed or velocity over time. If that's like this, what do we call that? It's constant acceleration, or what's the other term? Uniform acceleration. Excellent. However, if your speed, and if your acceleration is constant, then your speed or velocity is traveling like this. Because here the slope is, 5 kilometers per hour per second, 5 kilometers per hour per second. This is that graph that I called out to you, okay? And if it's changing at 5 kilometers per second every second, then that would be, goodness gracious, I can't hold this. I'm sorry, I gave you the wrong thing. Yeah. This would be a constant acceleration of 5 kilometers per hour per second. This was a constant acceleration of 0. Okay? Both of those are uniform acceleration. 0 acceleration is constant, or constant acceleration, both of those. And so here, you can do your average speed of either taking the final minus the, adding 2 of these, dividing by 2. That's not quite right, but okay, we'll leave that alone. Now, let's play along with some of the formulas again. Does anyone remember, okay, now y'all have to keep up when 3:15 gets here, right? You're not going to let me talk over that, are you? Okay, y'all are so good.
Right now.
What's that?
You're at 3 o'clock right now.
Are you kidding me?
No.
No.
I
It's
thought
3
you were. Huh?
It's 3 o'clock.
3 o'clock
Really?
right now. Yeah.
Goodness, how time flies when you're having fun. Okay?
Right.
Why are you laughing about? Okay. All right. All right. Someone remind me what acceleration was again? We just used it.
Final velocity minus final initial over time.
Final velocity minus initial velocity over time. Now, what's a little ugly about that formula? You like the denominators? You like fractional forms? Yeah, I could tell this group really likes the fractions, don't you?
No.
No? Okay. How do you get rid of that denominator? Multiply both sides by time. Here it wipes that one out, and you have V final minus V initial is equal to acceleration times time. And if you only were interested in what the final velocity was, you could add the initial velocity to both sides. And here's another new formula. V final is equal to, I'm going to put V initial in front now, V initial plus AT. So from our simple little acceleration formula, you can now derive another formula, V final. This works well if you know initial, final, and time, you can get your acceleration. But what if you know your acceleration, time, and initial velocity, but you want to know how fast you're traveling to the end? Then this is the better one, okay? Because that tells you what you're looking for, okay? All right. So let's do example 2.3, okay? All right to erase? Okay. Example 2.3. A bicycle moves from rest. Okay, we'll get back to that in a minute. What does that mean anyway? From rest. Wasn't moving, so what could you tell me? What characteristic of one of our favorite parameters could you tell me?
The initial velocity is 0.
Yes, that means the VI is equal to 0. Sometimes they call it V0, and I started to write that, but I said, no, we wouldn't call it VI. VI is equal to 0. That's what from rest means, okay? Now, okay, let's move on. Moves from rest to 5 miles per second. Wow. Meters per second. That's what I was going to say. That's a good bicycle. Okay, 5 meters per second in 5 seconds. Okay, what's 5 meters per second?
Wow.
That's your final velocity. It's a velocity because it's meters per second. This is 5 meters per second. What's your 5 seconds here? What's that? That's your time. T is equal to 5 seconds. Okay? What is its acceleration? First formula we had recently. Acceleration is equal to, what do you say? V final minus V initial over time interval, dt. Okay? And V final was 5 meters per second minus V initial was 0. I can even do that one. Meters per second. Divide that by 5 seconds, and what do you get?
1 meter per second.
Say that a little louder.
1 meter per second.
1 meter per second.
The meter is squared.
No, not the meter squared, second squared. You have 2 seconds. Meters per second per second. That's meters per second squared. You could write this as 1 meter per second per second. That's like it shows up here, but you can shorten that to be meters per second squared. That is a decent acceleration. That's a great unit for acceleration, meters per second squared. And that's what they got in the book. Good for them. All right. Let's go to example 2.4. Let me clear this. An automobile uniformly accelerates from rest. What does that mean? Yeah, what's 0? VI is equal to 0 from rest. Okay, accelerates at 5 meters per second squared. What's that a measure of? Say again? Say again? I think someone said it. That's your acceleration. Look at the units. It's got to be acceleration. Okay? For 6 seconds. What's that a measure of? Time. Okay. What is the final velocity in meters per second? V final would be what? You remember that new formula? You could go back and drive it if you don't. Anyone remember it? V initial plus AT. Now think about that. This is what you're going to begin with, and then this is how much you're increasing it, because that's what acceleration is, increase of velocity over time. So that's the amount of increase of velocity that gives you your final velocity. Okay? So plugging in, I can plug in the 0 here, and that's in meters per second, plus acceleration of 5 meter per second squared times 6 seconds. Okay? And this will be, I'm going to leave off the 0, okay? This will be 5 times 6 is 30. And this second cancels one of those out, only one of them, okay? And that leaves you 30 meters per second. That sounds like a great unit for a final velocity, doesn't it? I can't put my F there. There we go, sort of, okay. 30 meters per second. Good for them, they got it right. Okay. Now, how are we doing on time?
You got about a couple more minutes.
Really?
Yeah.
Okay. Let's see what the next slide is. Okay, this was that formula I was showing you before. I can't remember if I showed it to you on here. The average speed, as long as it's uniform acceleration, constant straight line acceleration, then it's V final plus V initial divided by 2. Okay? That's equation 2.3 on page 31. Now, at the top of page 31, there's a thing on science and society, transportation and the environment. Hey, that's where y'all live, isn't it? Okay? Good little blurb to read and some questions to think about. You might not agree with all this, or you might agree with nothing, or you might agree with every word of it, but it's still a pretty good thing to think about. And I think since we only have a couple minutes left, we will stop and pick up with example 2.5 next time. Is that okay with y'all? And then, can't get this set. We'll do 2.5 and 2.6, and then we'll move into forces. Okay? Okay. So, I'm going to stop the recording. All right. Each team has 3 different size circles. Okay? You have two of them, you have big metal circles, and I'm about to trash my computer. Okay. 2 large circles. The other one has a large cup, the top of the cup, not the bottom of the cup. You see it? The glass, the plastic thing right there? You see? Okay. That's your large circle. Your small circles are the dishes-like thing. Hold up the plastic thing. Yeah. That's it. Everybody see it? Everyone's got one of those. That's the medium circle. And everybody has a small circle. That's the little thing there. There's your small circle. Everybody see the 3 circles?
Yes.
Got it? Okay. You got lots of people per team. So I want, okay, listen up. Everyone will draw a single circle. Don't get more than 3 little circles. Don't get more than 3 medium circles. And don't get more than 3 large circles. Now that's a total of 9, and you have 7 or 8 people per group. So what that means is that a couple of you will draw 2 circles. But otherwise, everyone will only draw 1 circle. Okay? So trace one of the circles on the thing like you see here. Now there's plenty of paper there. Okay? But there's only 3 devices. So once you've drawn one, pass it to somebody else, pass it to somebody else. Don't get more than 3 circles of any one size per team. Okay? Okay? So you draw the circles, and then using a ruler, you will do your best to determine the diameter of that circle. And measure the diameters in centimeters or millimeters. Don't use inches. Centimeters and millimeters. Okay? Understood?
Yes.
All right. Now, 3 people will draw 3 of the same size circles. You just keep passing them around. You got 3 circles, so keep passing them around until you get 3 circles of each size. And like I said, 1 or 2 people will have to draw 2 circles, make them 2 different size circles. But everywhere else will be just 1 circle each. Each team, 3 circles of each size. Okay? And you do your own measurements. Don't depend on your neighbor's measurements. You do your measurement of the diameter of that circle. Now, when you get those measurements, you turn to the back part of the lab. That's page 23, near the back of the lab, and that's where you'll put in your measurements of the diameters. And you see small circle, medium circle, large circle. Okay, is everyone listening now?
Yeah, where I am.
Okay. No person draws more than one circle of any one size. Pass it around till you get 3 circles. No team should have more than 3 circles of any one size. Somebody will have to draw a second circle, and that has to be a different size circle. Get 9 circles, 3 of each. You got 7 or 8 people, so manage that however you want to. And record the diameter in centimeters or millimeters of those circles. Small circles in the first box, medium in the second. Now, if one person's measurement is way off from the other 2, go back and measure it again. Okay? You may be using the wrong units. Okay? And then once you got that done, I will describe to you how to do the circumferences. Okay?
Just like 4 centimeters. Thank you.
This lab number 2, right? This lab 2, Dr. Fowler?
What's that? This is lab 1. First lab is lab 0.
There you go.
Normally I don't have a lab 0. That's something for you to do.
I do not have a meeting.
I
I got 14 labs. No one has ever told you that. It's like 4 centimeters in that first one. Science.
And please, if you have questions, ask questions. Don't do something you're going to have to repeat. Ask the questions to find out what you need to do. Let each person measure his own stuff. You only work together as a team at the end, but you work individually and do your measurement.
Say something else too. 4.1. 4.2 is you said centimeters.
Now I got it. He's taking your measurement.
He said centimeters.
Got them done already? What's the date part? You already done
I'm
yours?
just saying what he said.
Oh, okay,
He
good.
said either centimeters or millimeters.
Explain the reason.
Alright, done. 41. What are the measurements for the other things? 1,400 or 140? 140. Yeah, don't you screw me right now. Did everyone else do that? Everyone got 90?
Yeah.
This is dividing line.
Calculator's time. 128.74. I'm changing your answer.
Okay, when everybody's got the diameters measured, let me know and I'll talk about circumference, okay? Y'all got it? You ready? Okay, if everyone will listen up, you can get back to you doing diameters in a minute, but the people who drew the circles, now, someone hand me one of the circles, okay? No, one of the actual things you drew. Okay? Ooh, you gave me the hard one. All right, give me one of your long strings. Someone give me a long string. Okay. Now here's how you do, watch out folks, here's how you do your circumferences. Okay, you need to wrap around the exterior, and you can do it any way that you come up with good answers. This is not cooperating well because there's sort of a bulge right here, but I think I pulled it out. And then it looks like they meet right there. Okay? So then I take this, point right there, and then I measure that length. That's how you do. You got your measure. This may be, I can't remember if this is more than 12-inch ruler or not. I think it is. This one you have to use your meter stick. Oh, that's too short, right? No, let's just hold it up.
Stick.
Yeah. Use the meter stick. And again, use in the metric side, to the nearest centimeter or So everyone who did a circle, do your diameter. You do your circumference. If you did a medium, do a medium. If you did a small, do a small. If you do a large, do a large. And then use that. If you have the big metal ones, you're going to need the meter stick to make your circumference. And then record your circumference underneath the place where you recorded your diameter. Okay? Now, your numbers should be similar. They don't have to be the same, but they should be pretty close. Okay.
What did you say you got?
The large circle is 439.6. The medium circle is 282.6. Medium circle is what now? 282.6. We can talk some poor little girl coming over to you up there. Yeah, she doesn't know what she's in for. Yeah. The old digging down. What is this ratio of C divided by D? That's the corona. Someone else mentioned that to me. No. Hey, measure your damn self. Do it yourself, Barrett. I know, we gotta have 3 people. Barrett, you could do it yourself. I've already done everything. Oh, do it again. Alright, well. Hey, we're gonna put some acid on it.
Hey, no acid in this class.
It's 3.4 all the way across. All the blocks. What's the average C over D? Experimental error. No. We are perfect. Yeah, he's not right. You did the math. You did the
What's that?
The box.
Top of the cup. That's your big circle.
Is this our cubes?
all right. Which y'all have, medium or small?
King one is
Yeah, it's on the next list. You don't even know you have it. What's that? Yes, it is. Okay, so has everyone measured all your diameters and all your circumferences? Oh, wonderful. Okay.
Did y'all see our one this morning?
All right.
One of the first year students didn't put the one.
All right. Now, okay. Did you get fairly close, not necessarily the same diameters and circumferences for each of the three circles? I mean,
Yes.
okay, they were fairly close. Okay, and you finished all 18 measurements, right?
Yes.
Okay, let's move on to area and volume ratios. We'll do the calculations later. We'll either sit down and do them in here, or we'll do them up in the classroom, or it depends on what time we have. But let's get the measurements made first. Okay, so move to Part B on page 16. Part B on page 16. Okay, now, each team has a box of cubes near you. Here's this team right here behind you. Here's your team right there. And there's your team right there. You see them? Okay, what you to do is get one cube out of one of the boxes, okay, and measure the length, width, and height of that cube using your ruler measurement, and again use either centimeter or millimeter scale. Be sure you put your units down. Pick a single block from one of the boxes, okay, and measure length, width, and height. Okay? Is everybody listening? Okay? Now, once you do that, notice that each cube has 6 faces. Top, bottom, right, left, and up, and front and back. Okay, 6 faces. So the size of a cube is also called a face. 6 identical faces. Okay. The overall area, surface area of the cube can be found by measuring, this is on page 16, the length and the width of one face, and then multiply those together, and then multiply by 6, the number of faces. So that's the area of your small cube, and that goes in data table 2.2 on page 23, the bottom part of the page. The small cube. Okay? Each team only needs one cube from one box to do the first one. Okay?
Oh, alright, so we need to put like all of these away.
Okay? Okay, all you need is one cube from one box per team. Yes.
How do you know which one's the small?
Pick either one. They're all the same size.
Oh my god. This is small, maybe a large.
Okay, you put it under small. This is small. I'm only talking about small here. Okay? Now, y'all have to finish making your diameter measures, haven't you? Okay, well, this takes time and you need a lot of time for it. And it's really suspicious when all the numbers are exactly the same. Okay. Well, these three are the same.
There we have one down there, so we don't have that one.
Okay, there we go. Okay, good. Okay. So,
They're not all the same.
what's that? The centimeters or millimeters of the measure. Millimeters going to give you bigger numbers, but it's okay. If you have any questions, though, please ask. Okay, once you got your small cube done, okay, then you need to calculate the volume of that small cube. You can wait and do that later. Write down, now let's go on and calculate the volume while you're doing it. If you have any questions how you do that, ask me, okay? Now, I'm going to show you what the medium cube looks like. Okay, I'm going to borrow some of yours if that's okay. Okay, is everybody watching?
Yes.
The medium cube, you have 4 cubes on the base and 4 cubes at the next level. You measure its length, width, and calculate the area, multiply by 6, and then you calculate the volume. Now you need to get them lined up. I didn't. But basically what you can do, double the length, double the width, double the height, and now that doesn't mean you double your areas and volumes. That's why you need to calculate those to see what kind of areas and volumes you get. So that's the medium cube. Okay? I'll let y'all play with it as you want to. Okay? What's that? The large one is 3 by 3 by 3. You got it. That's why you need all the boxes. Believe it or not. Okay, are there any questions so far?
Do we have that ruler touch?
Yeah.
You know, honestly, you can just take 2 blocks. Yeah. You can just do 1 and
What's that?
Are you gonna bring out a different block?
No, I mean, all the blocks are the same size. So if you've done the 2 by 2, okay, you got you calculated the volume. Okay, wait. What is that?
Wait, that's the medium.
Huh? Oh, okay. How did you get it? Okay. And how did you get yours? Right. That's it.
I just know it's really.
What did you guys get for surface area?
You calculate the volume. It's good you have this down. You need to calculate the volume too. Everybody know what the volume is? It's not how loud you're talking. What is the volume? Length times width times height. Okay?
You know what, bro? I believe you. I believe you. So how do you get that?
You were measuring in centimeters?
It would be. It's 50 across. 50 square. Would be the times the area. Would be the size. Yeah. 50 times 50. Yeah. 50 times 50. Times 6. So it's 50.
Yeah, that should be about right.
15.
So how we got that number wrong. Take off the 9. It's 3,000.
Okay, I was about to say, y'all.
Volume is correct. Volume on the small one is 15,600.
Alright, how you get volume?
Again, if you have any questions, please ask. Don't guess. Don't assume. Back when I was in the Navy, they had a special phrase for assuming. Have you heard it? Oh, yeah. That's it. Okay. Never mind. Okay. It was a naval term. Take the first three letters out of the fourth letter and the last two letters. Right.
So funny.
Huh? Oh, by the way, it's after 3:45 and someone let it skip by without telling me. That's all right. I'll forgive you this time, maybe. Okay. I see Drew still here. Capri is still here, right, or not? Okay, good. Okay. I can't see everybody. Lydia Kate Caddis hasn't come in yet, has she? Cameron J. Danzy hasn't come in yet, has he? Brianna Davis hasn't come in yet, has she? Jacob Dove is still here. Kaya is still here. Sam. Okay, yeah. I'm just learning names and faces. Okay. Tarsha is still here. Gunnar is still here, right? Where is it? Right there. I see you now. Okay, I saw you earlier. Okay, Eric, I think we lost, didn't we? Yeah, Eric Hill is not here. Zach is still here, right? I saw you somewhere. There you are. Jeff Jones is still here, right? Okay. Kurt Jones. Kurt? Yeah, he's here. That's right. I know who he is. Edward's still here. I got you. Okay, Katie hasn't made it in yet. Miss Lewis left. Jason Little I saw somewhere, didn't I? Right there. No? That's him. Yeah, I thought it was. Okay. Scott Christopher Lucas has never made it in. Ian is still here, mostly. Okay. Josh is still here. I see you. Zane is here. Got it. 3 by 3 by 3. And that's going to use almost all your blocks. Okay, people have moved on to the large blocks, which are 3 by 3 by 3. It's going to take almost all of your blocks. The large block is 3 by 3 by 3. You got 2 by 2, right?
Yeah.
That's your medium. Do your large. 3 by 3 by 3. David's still here. And Anaya is still here. Jacob Porte is still here, aren't you, somewhere? Okay, there I see. Wait, no. Yeah, okay, that's him. Okay. Jose was right here. Tiffany is in the back somewhere. There you are. Okay. Perrin. Okay, Perrin Reserve. Got it. Okay. And Cash still here. I see you. And Chad is mostly here. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23. That's right.
Just remember that, Aaron. You are not my favorite.
Okay.
Tornado. And the coronavirus before everybody else. The coronavirus is fake news created by the media. Yeah, you know, so long as they shut down schools. They're going to shut down the election polls 4 more years.
What's that?
4 more years.
Really? Wow. You mean University of Tennessee in Knoxville? Wow. Are they doing online or what? Online?
I think they got a 30-day suspension.
All
Wow.
Ivy League schools are suspended until further notice.
What's that again?
All the Ivy League schools have
Really?
Their students are not allowed on campus.
Yeah.
Wow.
They've sent all their dorm students home.
Wow.
You need to take your multivitamins and your vitamin C and your probiotics.
You just wash your damn hands. Like you should be
Do that
year
too.
round.
Yeah.
I wash my hands.
Yeah.
I ain't talking about you.
Yeah.
I'm not talking about you.
Okay. Hey,
Vitamin C
and,
and your
and another thing you may notice I'm doing is practicing social distance. Okay.
Hey, so, they said they won't allow teachers to go out of state. What happens if a student goes out of state? Do we get that 14-day suspension too?
Is this from here or
Yeah.
somewhere else?
That is straight up from here.
Wait a minute. I haven't heard this.
Yeah, our instructor said it.
When?
Today.
Today. Huh? Really? Yeah. You mean spring break, no one can leave the state. Is that what they're saying?
Well, I mean, I live in Mississippi. I'm going home
Yeah.
today.
Yeah.
Our instructor said that he was told if he went out of state and then came back, he had to self-quarantine at home for 14 days before he could come back.
Yeah.
Wow.
So yeah, I'm going back to Mississippi tonight, and
Yeah.
I'm coming back Sunday. So I'm gonna
Yeah.
self-quarantine myself. I'm gonna self-quarantine myself in Birmingham for 14 days, and then go home and try again. And then go home and try again.
They banned all flights from Europe to the USA.
Okay.
They got one case a month.
For a couple
That's
months. Yeah, for 1 month.
Yeah, dude.
Yeah, he straight up executed.
Point blank his ass.
He was just like, bam.
Too bad. I can think of some people I wish were in Europe now. Okay. Never mind. I didn't say that. Maybe they can get on a cruise ship and go over to Europe. Okay.
Hey, this is the time. Everything's on sale. Round trip to Miami, $89.
Wow.
Yeah, round trip.
I also heard, but I guess faculty can't take advantage of it.
It's
American Airlines.
I also heard there were great deals at Disney World.
Great deals at Disney World.
Yeah, I'm gonna see Mickey Mouse for $5.
It's $46 round trip to Los Angeles from Atlanta.
Right.
But the thing that I can't figure out is why do they think the other states are in worse shape than Alabama?
I can tell you. I guess we might be in Allstate hands, good hands,
That's what?
I said, I guess we in Allstate hands.
Right.
We in Allstate hands. Hey.
I've been hailing today. I've been hailing up.
They come back 2 weeks from now.
I've been through about anything or feels it for you guys.
You know what? Let's go with that.
That shit goes everything. See the island this morning.
I'll take my truck
Yeah.
now.
Have you ever done that?
I'm not sure if I
Alan sprayed the nest.
I sprayed a rat with it. $250, $66 to go for round trip to Miami for a week.
You gotta look at it different.
Unless you're an instructor.
What do you want?
I don't know about that. My flights are stuck on.
Okay, how are y'all doing? Are y'all through?
Yes.
Oh, okay. Let's get ready for part C. Okay? Now, part C, you're only going to do
Oh, wow.
one measure. Okay? I mean, one of these columns. Okay?
One column. Yes, sir.
Yeah, okay. Now,
Oh.
if everyone can listen up, you can go back and do, if you're a little behind, you can do your measurements in a minute. Let's go to part C, which begins at the bottom part of page 16. Okay? Who has the medium-sized container? I think it's this group back here, isn't it? Yeah. So hand me that container. No, okay. So what you're going to do, I'll need a ruler. Anyone got a ruler I can borrow from mom? Okay. Now here's what you do to measure, and let me Okay. Now, let me tell you where you're going to be putting your measurements. Okay? The small container, which is this group over here, you're going to put your measurements in on page 24 in column 1. Okay? The medium beam, that's the one back here, you're going to use column 2. The large container, you're going to use column 3. Okay? So, the length of the container. The length of the container will be, okay? This is a lousy ruler, okay? I'm going to start from 10 here.
There's the
Now,
large container.
listen up, people. Okay. Because these containers aren't perfectly square, they've got a little bit of an angle on one side. How you compensate for that is measure about midway the container. That way you're going to take the average, and that's going to come up about the same. And I'm not going to give away, I'm going to make up a number here. It's not, let's say 18.3. That's not what this is. But that's going to be your length. Your width is from here. And again, midway will be a good way to measure it. Okay? I'm just going to make up something here about 4.5. Now, that's not the answer. Okay? And then the height, now this is a little tougher. Okay? You got a little curvature at the bottom, so try to line it up the best you can. And that's going to be maybe 4.2 or something. I'm just making up numbers here. So get your best, but use the middle of the container and be sure that you get a length, a width, and a height. In centimeters. This one says centimeters. Don't use millimeters. Use centimeters. I think I got this from y'all and this from y'all, right? Okay. Now you got 3 different containers. You got a little one, you got the medium one, you got the bigger one. You found it, yeah. You see it over there? So do your measurements, length, width, and height.
Big container.
Hey.
No, are you through with them?
Yes, sir.
Okay, thank you.
All right.
Well, I can't see your question. Did you get them all back in here?
Yes, sir.
Even in the right order? That is superb.
Alright, length of container.
Fantastic. There we go. You even got them closed properly? That's wonderful.
16.5 centimeters. Curse you.
Did y'all finish with your circles too, or did we ever go back and finish those? You got them all. Okay, I can take the circles and the strings if you need. One more.
8.75 centimeters.
And you got all 3 strings. Deal.
You can't. Right, 3 centimeters.
Again, don't guess. Ask questions if you're not absolutely sure.
Three times 8.75 times 6.5. What? Do all of them?
Find the max. Mass is right, isn't it?
Zero that bad boy.
I can't.
No, it's not mass.
It's the weak
That
side.
is right. That really is a weak.
That's like a straight up weak side.
Alright, so I just have to weigh this?
Wait, do we measure?
Oh, it's something like 30 grams.
Yeah, 29 grams.
Container that holds
Got
water.
a whole ounce.
So the top is just in the way.
What is the mass of container? Oh, is there one full of water in it? No, we have to fill this with water.
Midway.
Does the same work? No, we have a large container of water in here. There's water in the bucket. I know. Leave me alone. I'm trying.
Put it on the scale and then pour the water in.
Yeah, but the lid won't stay on. So I can't hold it on the scale and the lid. That's not all the way up. You see this shit lying right now?
All right, I take it that some people are already doing some measurements, right?
I'm not playing the penny game, bro. It's already. This is as
Oh.
much water as it.
All right. Did you measure the mass of your container?
463.
Okay. Empty, right?
7 grams.
All right. And then you measure the mass of the container with water, or your that's your all right. Right there. Okay.
Mass of water. So,
We always pour water on the scale. 434. Measure the volume of water. You gotta put all that water in those tubes. There's no way that's happening. There's no way.
Don't listen. I hope there's a pipe for
You just gotta take what's in the container.
Are y'all using?
Oh, yeah.
Fuck, man.
We haven't yet.
Oh, you're still doing your measurements.
Oh, yeah, teamwork.
But there.
I am.
Did not work.
Now, don't overfill. George.
Hey, bro, actually, we made some
Oh,
banging.
damn.
Okay, we got another one.
We made some banging food. Hey, bro, we cook fried rice and shit all the time. We grill. You ever put a glue in the shower?
That's offensive.
Every time, like you in the shower.
Okay.
Josh says he doesn't want to go to my friend's house to shower.
This one's right at 2 feet. That's
Oh,
scary.
okay. You've been living right.
Uphill, not science.
Look what Josh did know. He decided to go to shower.
150, 155, every, okay, 150, 60, 70, 80, 90, 100. So every little line there.
Here's all right. First of all, you're Orthodox Jewish, so we're not like partially.
All right. Have y'all been pouring into your, okay, where are you in your measurements? Okay, you've already done the measured volume? Okay, y'all are moving along. Okay, you understand what it's asking for then? Okay, they give you the line numbers and everything. Number 4 is ratio of cubic centimeters, which is up there on number 4, to the volume. Okay, by the way, yeah, to milliliters, and the milliliters are down here in number 8, right? Ratio of number 4 to number 8. Right?
What time?
Number 4 is cubic centimeters, number 8 is milliliters, right? Hopefully they're pretty close to each other, are they?
106 to 125.
Rams divided by
Okay.
90.
Not as close as I'd like, but that's okay.
Oh, God.
That's okay. Which is smaller, which is larger?
Mass of water, or measured volume of water is higher.
1.27.
Okay. Must have rounded a little on your, but that's why taking three measures is okay, but taking one measure is usually a lot better.
134 divided by 240.
Bro, that's some kick in there. Ratio.
1.26.
And then number 9 is the ratio, I'm sorry, number 10 is ratio of mass of water. That's number 7. Now, mass of water, you subtracted 5 and 6, right?
You dump this water out there?
Okay. So it's the mass of water divided by the volume of water, which is number 8. So count 7 divided by number 8. Now, what's that? Yeah, but we gotta get the other measurement first.
That's the short.
What you need to do is come over. Are y'all through with the scale? Okay. You measured your volume yet? Is it pour into your?
Mass.
Oh, no, that's a bad scale. Where's your graduated soil? Everything graduated soil.
Let the mullet flow.
Oh, there it is.
Okay.
Oh, okay.
Let it flow.
Now, I think an easier thing.
I'm just
I should definitely take a video of this one.
From now on, class ends at 1:30.
That's what we're at.
I'm down.
What's Josh? I started at 1:15, Josh. That's not possible. We didn't get here way longer than 15 to go. We definitely got back in time. It's 4:30. No, you don't. Have however long it takes you to finish the test.
Yeah, we're not taking the test today.
Why are we not taking the test today?
Y'all are through with the scale.
I'm definitely taking the test.
Okay. Here's the
Yeah, but then don't you have to come take your I'm gonna just stay. You don't want to take your I'm gonna just stay in the yeah, the teacher assigned like all this work, and she's like, all of it is due to the last day of class. It's like,
Have you passed that class yet?
yeah, I retook it. Got a 98. I actually made myself do work.
Yeah, he's been taking it for half a semester already.
God, finished. Should be done by now.
He's not doing mini semester. He's not a mini semester, full semester.
Mini semester?
Oh.
I'm mini semester. You see that?
How you gonna touch him?
I just did.
Oh, wow. Yeah, just in case you didn't know that. Yeah, I think they're gonna give us
I'm wearing socks.
yeah, I got socks on too, so. Yeah, as long as you don't make eye contact. We also have this guy was like, definitely make eye contact. Definitely, yes. But it's a whole lot of shit now.
You're still willing.
Sam is just
What? No. Like, we can do this, but not that. Only time I've ever denied this is after doing this. You said bro, it's a joke. So you're saying you would never grab it?
This info from
Yeah, you get that? Okay. They're number 2, these are number 3, y'all. Okay.
Well, I promise you, there's no
Do it for
there's
you.
no mail in the
Okay. Y'all are block number 3? Okay, here's your block number 1 data.
We about to go on the plan.
What's that?
We about to go on the plan. We about to go on the plan.
Wait just a second.
Alright, nostrils, just because your nostrils make it
Y'all
sound.
just take a quick break from what you're doing now. You're
I mean, if I
gonna-
had 4-inch diameter.
One data. This is for number 1. You're number 2. Okay, number 1. Okay, y'all already got number 1, so don't worry about it. Number 1, length of the container, 9 centimeters. Lieutenant getting this? Okay, number 1, width of container, 3.8 centimeters. Height of container, 3.1 centimeters. You're going to calculate number 4 on your own. Number 5, mass of container, 7 grams. Number 6, mass of container and water, 118 grams. You can do all the rest of the calculations on your own.
Number 1.
Super good. Yours? Okay?
Okay.
Team number 3, use yours. You write mine. Okay? Are y'all ready to record number 3? This is you 2 things. Length of container, 16.5 centimeters. Width of container, 8.75 centimeters. What precision, okay? Number 3, height of container, 3.0 centimeters. You calculate the volume. That's number 4. Number 5, mass of container, 29 grams. Number 6, mass of container and water, 463 grams. Okay? And you can calculate from there.
We need number 8.
Huh?
We need number 8.
You need number 8.
Yeah, measure.
Oh, measured by, oh, you're right. 340 milliliters. Did I give?
That was for the first one too.
120.
Okay, 120. Number 8 for number 1 is 120 milliliters. Okay? Y'all got more than
Same
enough
way
time
you
to do
calculated
that?
yours.
All right, you have that on the right? Okay, don't do number 8. You're at 784, right? Let me show you a good technique to do that. Okay? What I suggest is dump this water. I will do that for you. Okay? Very carefully, for the water in here and here, let's get it in there, pour it carefully. Okay, it'll be just a minute on the last group. Okay. Let me, for purposes of people at home, read out those numbers because I'm not sure you can hear it here. I hope you copied right? Okay. For container number 1, the length was 9 centimeters. This is on page 24 of your lab. The number 2, width of container, 3.8 centimeters. Height of the container, number 3, 3.1 centimeters. You calculate number 4. Number 5, mass of container, 7 grams. Number 6, mass of container and water, 118 grams. You calculate number 7. Then number 8, measured volume of water, 120 milliliters. For container number 3, length of container, 16.5 centimeters. Width of container number 2, 8.75 centimeters. Height of container, 3.0 centimeters. You calculate the volume. Number 5, mass of container, 29 grams. 6, mass of container and water, 463 grams. And measured volume of water, 340 grams. Did I say 463 or 363? Mass of container and water, 463 grams. And measured volume of water, 340 milliliters, 340. Now, I'll be giving you number 2 in a minute. Okay? You got number 2 measured yet? Okay, listen up for number 2. Okay, number 2. Length of the container. Number 1 is 13 centimeters. Width of container, 4 centimeters. Number 3, height of container, 3 centimeters. You calculate the volume. Number 5, mass of containers, 10 grams. Number 6, mass of container and water, 200 grams. And number 8, you calculate 7. Number 8 is measured volume of water, 181 milliliters. And then you do the rest of the calculations. Now, if you want to continue working here, you certainly can. If you prefer to go to the classroom, we can do that. But you're sorted together in groups here. Are y'all okay staying here? Okay. Now, what I would say, if you still have calculations to make in parts 1 and 2, hang on to those for a minute and get the part 3 done. Okay? And what they're asking you to do on 3, the reason I want you to do that here is because it's doing a graph on that one. Okay? On page 18, the top of the page, number 6, it says make a graph of the mass in grams, that's the row 7 data, and the volume in milliliters, that's the row 8 data, to picture the mass per unit volume found in step 5. Okay? Step 5 was on the previous page. Okay? So you have to do all your calculations first for the third part. So when you get ready to make your graph, be sure to ask me a question. Let me know when you're ready and I'll walk you through it. Except, there it is. I couldn't find the graph paper. There it is. And by the way, I just want to commend this group. Y'all are doing probably one of the best jobs. I haven't seen your results yet, but working together and getting your measurements and asking very few questions, y'all are doing a superb job. So way to go. So when you're ready, okay, I think that one team back there still working on some calculations. Okay. Maybe I can get their attention. All right.
No, Ford's typical conversion ratio is 0.
Okay.
Because he said, I see a contract coronavirus.
I'm going to Mississippi to contract it.
Okay.
He's just jealous.
Okay. What I'd like to hear first is what your range of masses are. So tell me what your numbers are. Line 7 from small to large. What are they?
111, 190, 434.
Okay, 434 is max. Okay, what I would suggest then is set your graph like this. Okay, you're going to be putting your mass on the vertical scale and your volume on the horizontal scale. Okay, and the volume you're using is the measured volume, I'm pretty sure, let me see. Yeah, the volume in milliliters, the row 8 data. Okay, so your mass, and by the way, here's what I suggest the scale to be. 100, 200, 300, 400, 500. Okay, and horizontally, 100, 200, 300, 400, 500. I think you'll be able to fit all your data within those parameters, right? So the mass in grams goes up here. The volume in milliliters, I think it is, goes across the bottom. Okay? So label your graphs and then plot your points. Okay? I think that's what it was measured in, wasn't it? Measured volume of water was in milliliters. Okay? The line 8 data. So your mass was in, in grams, and your volume in milliliters. So what I would do is go across here until you find your volume in, for that small container, in milliliters. Remember, each one of these blocks, the big block is 100, the little blocks are 10 each. So that's 10, 20, 30, 40, 60, 80, 90, 100. 10, 110, okay. Okay? So your volume here, your mass up here. Plot that point. Volume here, mass up here, plot that point. Volume here, mass up here, plot that point. You got 3 points to plot. The horizontal scale is volume, vertical scale is mass. And your ordered pairs are the numbers above and below each other on items 7 and 8. 7 is vertical, 8 is horizontal. Yeah, today's supposed to get to 78, wasn't it?
That's already on up there. It's like 81 right now.
Wow.
Yeah. Yeah, and it was like 100 degrees over here, so I don't know.
Y'all were turning and burning, huh?
I got tired of
Okay.
still sweating. There's a lot of people on Snapchat in Alabama right now. There's a lot of people on Snapchat now.
Okay, if you have any problems, ask. You okay? Now, you'll need your rulers again, and once you've plotted your 3 points, please, folks, this is not what you do. You don't connect point 1 to point 2 to point 3. You put your ruler down and use one of those see-through rulers, you know, the plastic ones, and get the best thing you can for a straight line, coming closest you can to all 3 points. Okay? It may not intersect any of them, but get the closest you can get for 3 points. Best straight line for 3 points. Are they fairly close to a straight line? I hope. Good. Yeah, did you have a question?
Yeah, I was see whether I'm doing this correct. So I plotted 118. Man, I plotted 120. And I went up
Not 118. Mass of water, 7. You don't want the container. That's the mass of water.
Okay, so we're just doing these two.
Yeah, yeah. This is XY, XY, XY.
Okay.
Horizontal, vertical, horizontal, vertical, horizontal, vertical.
So what I number the mass by?
I'm sorry?
What do I number the mass by?
10, 100, 100, 200, 300, 400, 500.
Oh, the same thing as
Is that what the ranges are on the other page? Yeah. Yes.
Alright, so what's the first question? This is like 118, 119, what just slapped there? Oh, wait, they're all in this drawing.
You can do better.
Just through these three, not all the way to the bottom.
Between those three.
Alright.
Oh, I did.
Okay, so alright, so we gotta go. 111, 190.
Whoa. Yeah, you've done well, but you see the see-through makes it so much easier. So you can, yeah, you can see if you can only see above with that one or below with that, but you can't see right. Okay. I don't know what y'all are using. Two perfectly good rulers. Anyone need a ruler?
I do, yeah.
What is that going to be?
You've already met it. Where's your data? Where are your data? Page 4. Okay. Here's the measured volume of water. That's from the vertical scale. I mean horizontal scale. And mass of water from the vertical scale. No, these two right here. These two. I would say that. All right. Now,
You started at 0 when you draw that line?
what's that? If 0 helps stay on the line, good. If it does not, just use a 3 point.
Go 3 or 4.
Huh? Yeah.
Like this, then that. No, you
Now you do one, the best straight line that gets closest to all 3 points. Okay, it's better to use a see-through. That way you can get close. Okay. I like it.
Huh?
I like it. I just wish you could find it.
Yeah.
Oh, well, yeah, that's true. 0, 0 is supposed to be important. Oh, I did.
You said it whenever it gets down to 4 pounds, go.
Click. Don't just swap it back and forth, right?
Well, that makes the equation
Pretty great.
I've got it for $16.
Pattern on today.
That's a very
Totally stolen.
Yeah. It's marketplace all the time. Mass is the rise, volume is definitely.
I caught some bullets.
So rise is the highest rise is 463, the lowest rise is 438, 436. So would that not be rise over the 4?
Yeah.
Oh wait, 434 is like, that's the mass special graph. That's a rise. That's like the rise of the entire graph.
just wanna let you
And
know.
then this is the run the entire graph. That's the part we went over. So it should just be run, divided by run. And that's whatever, 34 divided by 3.
Now, are people far enough along to, or you already are calculating your slopes? Or are you waiting for that?
That's what we're on.
Huh?
That's what we're on now.
Okay. You know how to do them?
Yes.
How?
Rise over run.
You got it. And especially if your two endpoints are pretty close to the same line, then you can just do rise, or you can use your data on your other sheet. Okay? But if they're not, then read it off the graph. The graph is the best thing to use, unless you can't tell any difference.
It says to start in the direction. It does say to start at 0, 0.
Okay, I can't hear well. Say again.
It says make a
Yeah.
line on. Are you supposed to do that?
You can do it too and see what your difference in slopes are if you want to do that. Oh boy, if the points don't fit, make the points bigger, huh? Yeah.
No, I
Just kidding.
got covered up by line.
Oh, I see. That's it. Okay. See what your slopes are.
So start it right here.
Okay, yeah. See how that
Calculate
yeah.
Start with your layer.
See with the ruler what you can do with that. Calculate the slope both ways and see what comes up.
Just say per.
Being closer.
You just put 0. It's always an acceptable. 0 is always an acceptable answer for experimental layer.
He's got the ASC back,
You would be if you worked for anywhere else.
Actually, forward's supposed to go back to that. Yeah. Do we get grandfather data?
No,
we just
absolutely not. You're gonna all take an $8 an hour pay cut until you get recertified.
No,
You put a point there.
Sure you can. At Toyota, if you don't recertify ASE, they'll cut your pay. Well, actually, it's a lot.
I'm on a contract before the ASC stuff was switched forward.
So why are you guys going back to ASE?
That's what I do very well.
How do we calculate our experimental error? How is the value
Okay.
high?
What you expect the slope to be.
Google.
No, so it's 0.2.
It's right behind you.
Because this is the expected value of the single guy.
Oh, yeah. Why does pi not have grams?
Pretty hard subtraction. I think you use the calculator.
Wait, what?
The calculated error is
Throwing my rulers around too.
What is a ratio?
The ratio is a comparison of two numbers in a division.
I'll run you. Go to.
I don't know.
Yeah. Okay.
No way. Okay. I just want to let you know, you can line my grill with the floor.
Exactly. That's what. It's supposed to say COD.
Divided by 9. But, as you get this out,
Because there can be more volume than
the circle.
Oh, more volume than what
Yeah, use the string.
I can't fill the circumference.
Why does pi not divide by
Diameter.
What is that circumference?
Sir, come here.
What's the purpose?
Here. Hey, front wire. It's just the correlation between two amounts shows number of times. Wait, just the relation between two.
Yes, I guess.
It's several examples of ratios and everything, your ratio and whatever.
So do you want us to leave the slope, put it in decimal form, or leave it in fraction but go as low as it can?
No, actually do a decimal.
Okay.
Yeah, because everything else is in decimal. Okay, you finished with the other?
Your ratio
The first two. The first table. Okay, yeah. Well, I mean, on the first one group is running. All right. Have most teams finished even your graph?
Yes.
Okay? All right. Now, what we got to do yet, and we've got about 20 minutes. You may not be able to finish this in 20 minutes, but you should be able to get far enough along so that you, and is everybody calculated slope and you know how to do that? You're happy with it?
I think I did.
Okay. All right. Now, a couple of points. Okay. When you look at your these experimental sheets here, one thing to watch for. That's not, folks. One thing to watch for are blanks. Okay. You see, everything's written on page 15 pretty good. On page 16 pretty good, except when you get to number 6 on page 16, the big blank under it. Look back at that and said, describe a pattern or generalization concerning the volume of a cube and its surface area to volume ratio. Now that's using the part B. That was the bottom part of on page 23. What you're looking at is the describe a pattern or generalization concerning the volume of a cube. That would be the middle line, right, to the surface area to volume ratio. That's the bottom line. So what's happening is the volume is going up from small cube to large cube. What's the ratio doing as you're going from small cube to large cube? Okay? So you need to answer that questions. Okay? So that's number 6. Be sure you put an answer there. All right? Then flip on over a page or two. Now, I saw some people doing this already. When you get to number 8 on page 18, calculate the slope of the graph, and be sure you put that calculation on number 8. Calculate experimental error, and I had one person ask a question about it. What is experimental error? That is measured minus expected, and the accepted is 1.0. It's a real tough subtraction to make. Okay? So number 8 has an answer, number 9 has an answer, number 10 has an answer. And then number 11 also. Now number 11 is your opinion. If you write an answer down that answers whatever it asks here, and it at least makes some sort of sense, whether you didn't think it did or did, as long as it makes sense, you get credit for it. You leave it blank, you don't get credit for it. Okay? Now, this is the only lab with a results page like this. In fact, not just a results page, a results 3 pages. Okay? So, someone had already heard asking, what is a ratio? Go back to page 15 and you see it's defined there for you. Right? All right. Okay? Now, did anyone realize what you were, okay? On number 2, the question for number 2, if you look again back at page 15, the very last number 4 at the bottom of the page, that has the answer to number 2, right there. Then number 3, number 4, number 5 are things that you answered just by the thinking. I said something wrong. A lot of the labs will have these, what do they call this? Results section, where you answer questions. Number 6, you answer a question. Number 7, you answer the question. What I meant to say was, this is the only lab with a problems section in it. The problem sections are on page 20 and 21. This, I don't want to say it has nothing to do with the rest of the lab, but it's completely separate. You didn't have an aluminum block with this thing. This is starting over from this block that you see right here. Okay? So starting on page 20, the problem there, you start with this block and you answer these questions. Number 1, number 2, and then over on page 21, it says make a sketch of the aluminum block. So do your best to draw that same block they have here. Now I would not darken in that one side like they did, but do your best to just copy that block on page 21. Just to make as good a copy as you can. But then what you do, show the area of each face in square centimeters. See, this one's shown just with dimensions in meters, but question number 2 says what are the dimensions of the block in centimeters? So you draw the same block here in number 3, but put the dimensions of the block in centimeters, but then calculate the area of each face in square centimeters. Does that make sense? If it doesn't, ask and well, I'll get with you. Then you keep answering those questions until you get to the end. Now, if you have questions, good thing to ask. Take advantage of this next 15 minutes you have to get as far as you can, so if you do have questions, I can answer them. At the beginning of class on Tuesday, I'll ask like I always do, are there any questions? If you've run into questions over the weekend when you're finishing the lab, answering those results and problems, if you've run into things that are you need questions about, that's the time to ask. In class on Tuesday when we first get here, that's a good time to ask your questions. The labs aren't due until a week later. That gives you, Tuesday to ask questions and then turn it in on Thursday. Okay? If you need more time, I'll give you more time. But don't let it get behind in your labs. Is there a question right now? I hear. Okay. Y'all are talking to each other. Now, either when you finish your lab or it gets to 5:15, whichever comes first, you can start your test. I don't want you starting it after 5:15, but if you can finish your lab before 5:15, fantastic. If not, work on it until then, and ask me any questions you may have, because that's what I'm here for. Make your weekend easier. Now, if some of you need to take this extra 15 minutes to work on your formula and equation sheet, you may want to do that. That gives you more work to do on the weekend. Yes? That's fine. Morning or afternoon? Afternoon.
I'll get out of 4 class to about 3. So
Okay.
I'll probably show up around 4.
Okay, I'll be, you know where my office is? Okay.
Yeah, I'm going to take mine Monday too.
Okay.
I'll be with him.
Okay.
Yeah.
He started at 0,
What's that?
He started at 0, on this slope, and I
Right.
started where we
Right.
were past that. It's max right now. His 1.25, mine's 1.4.
It's what?
Mine's 1.4, his 1.25.
This is better. I would use this.
Okay.
Closer you are to 1, the better.
All right.
Yeah.
This class was a little bit challenging. So, first of all, it's mere error.
Okay,
And I
wait.
know-
Have you calculated the slope?
It's
We need
there.
to do that first.
Do that first. But what I'm saying is, I'm go back because we need that as well.
Okay. Now, on this one, you also, okay, this is on here. Oh, here's the experimental error. See, this is the one on this one, okay? Where is it? Oh, it's here. Okay, that's it. There's it. Okay, this is this one. Okay, what you did here, you did the ratio of each of these, right? What you do is add these 9 together and divide by 9.
Okay.
And you get an answer.
Okay.
Okay? Now, it's looking like it's all going to be greater than 3, and you'll just have to see what the average is. And then whatever you get in that average, then you compare that to 3.14, because that's the actual value of pi.
Okay.
Okay? And your measured minus actual, that's your experimental error.
That's what you say. Actual measured minus. I wrote it somewhere.
Okay,
Hold on.
right.
This is my note.
Yeah.
There it is.
Yeah. Measured minus actual. Or accepted in this case.
Okay.
Yeah. Measured. You measured up here, slope up here, minus what your accepted value is here. That's your experimental error.
All right.
Okay?
All right.
That answer what you needed?
I hope.
Okay. If you have more questions, Tuesday, you can ask them. Yeah.
Is there by chance, or so I can take my test Monday during your office?
Yeah, of course there is.
What time are you at? I don't have access to Blackboard. For some reason, I'm locked out of it right now.
Really?
I've already sent an email asking for assistance, and I haven't got back.
Okay.
So, when are you at your office on Monday?
I'm there from 8 to 10 in the morning, and from 3:45 to 6 in the evening.
We're all coming in at around 4. I'm also going to come with them.
Okay.
I just need to borrow a classroom for him.
What's that?
I might just need to borrow a classroom for him. I need to get a whole classroom for him.
Okay, we'll find something. 4 o'clock is usually plenty of things.
And what is your office?
Where is it? Okay.
Yeah, it's right down.
Right down the hall. If you go this way to the end of the hall, before you hit the wall, okay, there's a stairwell at the end. Door just right before the stairwell, that's my office, 265. Right across from the orientation classroom.
I know exactly where that is.
Okay. There's a fan room, there's a stairwell, my office is in between the two.
Thank you, sir.
All right.
We'll see you
Now.
at 4:15.
Say again?
I said I'll be there somewhere around between 4 and 4:15.
Okay, I should be down there. If I'm not, I'll be back.
Okay.
Okay. Let's see, Monday, I don't think my work study student is here that late. So, you see what sometimes I do is up in the classroom, finish up, try to load things to Blackboard and stuff like that before I come down. So if I'm not there, I may be up in the classroom.
Okay. All right.
All right.
Thank you.
All right. Have a good weekend.
Can I start my test?
I guess so. Okay. It's
I
8
know
minutes
you don't like
early.
me, Dr. Fowler.
What's that?
I know you don't like me, but just bear with it. You're retiring soon, and I'm going to graduate soon. So
Well, I bet you beat me, don't you?
barely.
Really?
I'm going to graduate in the summer.
Summer? Yeah, you'll be a big shot. See, I won't retire until the 1st of February. So you'll be long gone and having a good time.
Oh, what a shame.
Yeah.
I'm going to get my EMT's license.
What's that?
I'm going to get my EMT's license.
Which one?
EMT.
Oh, really? Super. So you're doing it here?
No, I have a friend who's a manager at North Star EMS.
Uh-huh.
And they have a program where you can do it for like $500 and it's only a semester.
Wow, super. That's right. Do you have a point of equation sheet? You don't need one? Okay. Yeah, do you have a calculator?
16 million, 200,000.
There you go. And if you need to show scratch work, show it either on a different piece of paper or you want to do it down here or up there? Okay. Yeah.
I was just gonna do it down here.
Down here, that's perfectly fine. Okay, do you think there'll be any more questions, or should I start uploading the file? Any other questions?
Why does mine not have units?
What's that?
Why does mine have units?
Okay, well, how did you get pi?
Well, you did the ratio of circumference and diameter.
Okay, what were your units in your circumference?
Millimeters.
And what were your units in diameter? What?
Millimeters.
Wait, well then don't do that. Be sure you have the same units. Okay, did you say they were both millimeters or what? Oh, okay, yeah. If they're both millimeters, well then the units cancel out.
Okay.
And pi is a pure number, yeah. Okay, any other questions before I shut down the recorder? Are there questions? And by the way, the afternoon recordings usually won't load until the next morning. I don't know why, but they've been doing that. Yeah.
One more time.
Okay, surely.
Okay. You said once I calculate the slope from the graph,
Right.
which is here,
Right.
then I find the experimental error, which is measured by the
Okay, your slope is your measured, and the actual is
Is
this
the
one right here.
Oh, that's okay.
That's the actual right there. Now, okay, you see the other actual, that was for your other experiment.
Yes.
This is the actual
For this.
density of water,
Okay.
and this is your measured density of water.
Okay, now,
That's
remember,
right.
I've been out of school a long time.
Oh, that's
so,
all right. You're doing well, very well.
Slope, that's y equals m over, no, that's y, mx plus b.
No, okay. All right. Where's your graph? Is it on here somewhere?
In the very back.
Yeah. Okay. Now,
Did I do it right?
is that your point up
That's
there?
my point right there. And this is
Okay.
my point 1, 2,
Okay.
and 3.
Now, I don't know if this is a long enough ruler. Oh yeah, it'll do. Well, almost do. You try to get the best line from all those points. You got the best line for those three there, but you need them all.
Oh, for this one right there.
Yeah, but yeah, you see, I can't see there's one and there's one. So these two are below, those two are above, and they look like they're about even, right?
Okay, yes.
So draw that line. There's your best line.
Oh,
And then calculate the slope of that line.
okay.
Okay, see, they're not bad. Okay, calculate the slope of that line. Okay,
Yeah,
and
that's what I was asking is the formula.
okay, yeah, that's what I was just going to show you. Your rise is from here to there, from there to here. Well, this point right here, here's what I'm using, and you
Okay.
can use anything you want to. That covers really close right there, right?
Uh-huh.
So that is 400, 10, 20, 30, 430. Okay, and your run here is 3, 10, 20, 30, 40, 50. Well, I'll let you figure out. Look like 360 or something like that. That's your run, so rise over run.
Okay.
That's my ruler.
All right. Yes.
Okay. Anytime that you want to start your test, it's 5:12. It's getting close enough to 5:15. So when you're ready, I can give it to you. Or all of you planning to come back and take it later?
I'm taking it now.
Okay.
Yeah, I'm taking it now.
All right. All right, for me to shut down the recorder? Okay.